Hello and welcome to another day of HPG. Today is going to be the last day of the virtual part of our conference. And of course, after that, we're going to have an in-person event right before SIGGRAPH, so don't forget about that. Today, we're going to have a whole bunch of events, of course. Please check out the program for details. But I want to remind something to everyone in OEA here. Please remember to vote. Remember, we have two types of awards that require your voting. One of them is Posters Award. The other one is Papers Award. You can vote anytime. You can change your vote anytime. So please remember to do that. All right. Let me finish with the reminders. We're starting today. Now, today, we're going to start with some words from one of our sponsors, Intel. We're going to have a short presentation with Intel right now.
Hi everyone, good time of day. Thanks for being with me here at the fourth day of HPG. As you've seen yesterday, Naveen has presented the Alchemist architecture, and it's an exciting day, right? Because Intel is entering the market with a new discrete GPU, and this discrete GPU has a full-fledged DirectX 12 Ultimate feature set. And even beyond that, has ray tracing, it has a systolic array for AI acceleration, and many other features. And of course runs all the modern and legacy games. But we have just entered the market, right? So this is just the beginning. We have a lineup of future GPUs like Battlemage, Celestial, and Druid coming. And while we are gaining the momentum in graphics, Intel is just starting with the silicon, right? What we actually have is beyond on the silicon layer, we have the full visual compute platform. On the bottom layer, the compute layer, the silicon layer, we have Intel Core, Xeon, and Xe architecture, including Intel Arc, Arctic Sound M for data center GPUs, and other accelerators. But this is all just the hardware layer. On top of that, we provide the connectivity layer, which is the roads between these hardware nodes. For example, the Project Endgame provides the continual compute for games, where it shouldn't matter where you run this game. It will find the best visual compute, the best GPU around if it's available. But compute and connectivity layers are still pretty low level. On top of that, we are building the intelligence layer, which includes algorithms and solutions. And we have one API with multiple libraries, data parallel C++, and solutions for film, for example, such as Oscar-winning Embry, Open Image Noise, and other libraries inside the rendering toolkit, as well as for games, such as XeSS. So no matter what you do in graphics, you can always find an interesting niche, an interesting vertical, right? An interesting technology to work on, whether it's games, film, ProViz, or even the 3D internet of the future. But while we're actively building this platform, let me also talk about some problems that are tangential for high-performance graphics audience. As we've seen both from Intel and Patrick also showed some advances in path tracing, physically based real-time rendering is still a challenge. And it's a challenge both for games and movies and for other industries, right? So path tracing and physically based rendering is pretty high on our agenda Another interesting direction is content representation and creation. So how can we commoditize the content creation? How can we make it easier and more controllable? This is a very, very important direction. And then last but not least is a scalable visual compute that includes new pipeline, distributed rendering systems, level of detail, and of course all sorts of scalability and compression. Those are good problems to have, right? But what do we actually do, right, to solve these problems? So this year Intel has a few publications, 2 HPG papers that I would encourage you to check out if you haven't seen them, a Eurographics report and 1 SIGGRAPH paper. And we also give out our alchemists as awards at HPG, which you can use for your research and even try out some unique features such as hardware acceleration for shader sorting and the traversal shader support. So if you're passionate about graphics and these problems sound interesting for you, please consider joining us. We have multiple positions both in research as well as in software and architecture. And no matter whether it's games or movies, we have something interesting going on. Thank
you. Thanks to Intel for their sponsorship and awards this year. That was a great talk. Welcome everyone to the sort of technical portion of today's conference. We'll start in about a minute with Gordon Wetzstein's keynote. But before I do that, I just want to remind everyone to make sure during the day today, especially after the final paper session later today, make sure you use the award poll that is like up here, like on the top of just below the video and microphone icon, as well as the posters poll in a similar place in the posters room to vote for the papers and posters you like the most at this conference. Our awards, which will be announced later today, will be on the basis of your votes. That's the tradition at HPG. So make sure you make your voice heard, the papers that you like, the presentations that you like, the discussions that you liked, so that they can win the award. And we'll remind this to you multiple times during the day, and you'll have 5 minutes right after the final paper session to do that. And with that said, I'm very happy to introduce Gordon Wetzstein. He's a professor of electrical engineering and computer science at Stanford University. He's the leader of Stanford Computational Imaging Lab and a faculty co-director of the Stanford Center of Image Systems Engineering. I just know Gordon as one of the best researchers across the stack in augmented and virtual reality research. He has a lot to talk about: the future of XR, metaverses, how to make comfortable and more accessible experiences. And I'm sure you will really enjoy this talk. With that said, I'd love to bring him on the stage and begin his talk.
Oh, hey, everybody, and thanks for the introduction, Andrew. It's a great pleasure to be here. Hopefully everybody can hear me well, and you can see my slides too. It's a pleasure to talk to you today, and I would like to tell you a little bit more about some thoughts about what I think about is coming beyond the metaverse. Like, what does that even mean? So everybody's talking about the metaverse, and the metaverse is a really interesting concept. It creates digital spaces to meet people. It hopefully enhances communication for the better. It enables new forms of entertainment. And also AR is really something that can help augment human vision. So there's a lot of potential, and it's a really exciting time for computer graphics, really. Like, I've been part of the computer graphics community for the last 20 years now. And I mean, it's been around AR, VR as a technology for a while, but I think now is a great place and time to really push this one level forward. What I'd like to think about is not just how XR enables the obvious applications that everybody talks about, but thinking a little bit more about the human perspective of this and how to create perceptually realistic experiences that are also visually comfortable. And many of you are working on different aspects of this, so hopefully you get some interesting insights from this talk. Obviously, if we want to talk about perceptual realism and user comfort, we need to understand the user. And the primary interface between an XR experience and the user is typically the display. So the first thing that we need to think about a little bit more is the eye. And many of us, including Anjul and others, have been thinking about, how do we understand the distribution of photoreceptors on the retina, for example, to help design better graphics experiences and display systems. The photoreceptors are pretty dense on the fovea. They get less dense farther away in the periphery of the visual field. So we can use techniques like foveated rendering, for example, foveated displays. These are all fairly standard techniques that have been around the community for a while, but there's a lot more to explore still. And this is an interesting aspect. But there are other things about the human eye that are worthwhile thinking about. So one other aspect is the accommodation mechanism. So how does the lens, the crystalline lens in the eye, accommodate to different distances? And how does that enable different types of affordances and experiences? How does refractive errors and prescription in the human eye, how are those affected by the display, by the rendering experience? How do we make sure that the person gets the best experience with great visual clarity and the ability to accommodate at different distances? But we also need to study eye movements in general. If we want to enable gaze contingent paradigms, which is a big thing in high performance graphics for XR, then we need to think about not only building technology that robustly tracks these eye movements, but then also in rendering and display techniques that are able to leverage that information. Okay, so I want to talk a little bit more about these different aspects. And I mentioned perceptual realism and visual comfort as two key aspects of, let's say, our research that we focus on, but that are generally very important. So for human-centric displays. So perceptually realism, what does it mean? Like, think about it this way. If you have a mixed reality experience, we want to design this in a way that, fools the user in believing that the digital content is absolutely real. So in computer graphics, we've been calling this, photorealism, and we've achieved that maybe a few years ago. We can create images that are indistinguishable from reality. But there's a difference between photorealism in computer graphics and perceptual realism in VR and AR. Perceptual realism includes aspects that include, your eyes accommodating at different depths, chromatic aberrations, and many, many other aspects, the color matching, the high dynamic range, and other aspects that, are maybe not quite as important for photorealism in computer graphics. So you can think about something like a visual Turing test for displays that we need to pass. And you're probably familiar with the Turing test. So there's a computer and a human person behind a wall. The user only has a terminal to interact with them. And if they can't tell which one is the computer and which one is the person while they're chatting with them, then the computer passes the Turing test. So similarly, for visual Turing test for displays, if we display a virtual teapot augmented on a physical scene, if the user cannot tell which one is digital and which one is physical, then we pass the Turing test. But we're far away from that, and high performance graphics is one of the key aspects to achieving that, along with display system engineering and other aspects. Visual comfort is important because we want to make sure that people don't get eye strain. They have a visually comfortable experience, and VR and AR is not only for entertainment, for 20-minute games. It is used, for example, for surgery. In the Da Vinci robotic surgery system, the minimally invasive surgery systems, there are thousands of those already performed per year. And the surgeon actually uses an XR system to perform the surgery for hours at a time. So we want to make sure absolutely that there's no eye strain, and it's an absolutely natural and visually comfortable experience. So these are two super important aspects. And then the last thing I mentioned was eye movements. So eye movements include eye tracking, and eye tracking is something that seems like a solved area, like many in graphics, but the devil is really in the detail, and there's no real commercial eye tracking system, especially for AR, that works at the low powers required for all-day wearable use, that is robust enough to drastic changes in the environment, ambient illumination, that has the low latency that captures the eye movements at enough speed and latency to really capture microsaccades and all the subtle eye movements. So it's actually a really big engineering challenge at this stage. And there are some interesting new directions that I want to tell you about in this talk. So my group works on XR technologies mostly, or at least that's one aspect of our group. And that includes AR, VR displays, perceptually driven rendering, and also eye tracking technology in general. So these are some of the topics I want to talk a little bit more about. And there are hopefully some interesting ideas that are relevant to your research in here as well. So let's talk about the display aspect a little bit more. I know that this community doesn't necessarily work on displays a lot, but I think when you work on rendering techniques, keeping the display in mind is absolutely critical, because the two kind of have to go hand in hand. There's the GPU side, there's the rendering algorithm side, and then there's the display side. And sometimes for these emerging systems, it's very difficult to disentangle the three. So it's good to have an understanding of what's out there. To some extent, VR displays today haven't fundamentally changed, at least in their basic principle of operation, from the stereoscopes that were developed by people like Charles Wetzstein in the 1830s. So these are stereoscopic viewing apparatuses where you separate optically the two eyes and you present two different images rendered from slightly different perspectives. So these are stereoscopic displays. And the thing is, they have evolved quite a bit. They've become digital, they've become interactive, they've become shared experiences. But this is a grand challenge. The National Academy of Engineering in the US has declared enhancing virtual reality a grand challenge of the 21st century. So we need to continue to engineer this from all ends, from the optical side, from the electronic side, from the rendering side, from the GPU side. There is so many different challenges, which makes it exciting for us as a research community. One specific aspect that we've been working on in the lab is this idea of making this perceptually more realistic. And one aspect of perceptual realism is to be able to focus your eyes or accommodate them. The challenge was most existing VR and AR displays is that they have a micro display that sits behind a lens. We call this a magnifier design. And what that means is that there's a fixed distance at which this virtual image appears. So you can use the Gaussian thin lens equation or the lens maker's equation on the lower left to predict at which distance the magnified image will appear. To some extent, this is basically just a magnifier lens. There's a lens that magnifies the image, but it also moves it back in depth so that it is appearing at a comfortable distance. For example, something on the order of 2 meters. So the focal length of the lens and the distance between the physical microdisplay and the lens determine, to first order approximation at least, where the virtual image will appear that we actually see. Now, this is a really simple design. It's used by pretty much all commercially available AR and VR displays, but it has a lot of problems. It is a fixed focal plane display, so it doesn't support focus cues. What are focus cues? Focus cues is the inherent ability of your eyes to accommodate or to focus at different distances. So in the real world, we look at different objects at different depths, and our eyes will accommodate to these depths, similar to the autofocus of a camera. And that is really important. It's not just a thing that brings objects in sharp focus and makes them appear sharper with better visual clarity, but it's also important for comfort, because there's this vergence accommodation conflict where our eyes verge, driven by the disparity we render into the images. But if the vergence doesn't match the accommodation, then that creates nausea, potentially eye strain, and other things. So a lot has been said about the vergence accommodation conflict. I don't want to necessarily go into it too much. I'm just trying to emphasize that accommodation cues are important. So my lab has worked on this for many years, so I'll just give you a brief overview of some of the things we've been touching upon over the last couple of years. There are many different technologies that could be used to address this challenge. Probably the simplest one are gaze contingent varifocal displays. So if you know what distance the user looks at, you could try to adjust the focal plane of the display to exactly the fixation distance or the gaze depth. And this is something that we explored in 2016, 2017. We had the SIGGRAPH eTeX. We published a couple of papers at various conferences. And this was also picked up by Facebook, which is now called Meta. The idea is to dynamically change the focal plane. This is like, think about this as an autofocus mechanism for the display. It's very, very effective, but you do need eye tracking and it needs to work robustly. There's this idea of using light field displays close to the eye. So the light field in this case would project multiple slightly different images into different parts of your pupil. Very similar to a stereo image where you have one image picked up by each eye optically, but here you want to pick up multiple images over the pupil size of a single eye. And so Magic Leap set out to do that. I consulted with them for a couple of years, and then I co-founded a company called Raxium that was working on micro LED displays for applications like light field displays close to the eye and other applications. So we've been working on these types of technologies. They don't necessarily require eye tracking, and they're really, really interesting. But, I've been giving talks about these topics many times, so I would like to focus on a slightly different topic that we've been focusing on in the lab for the last 2 years or 3 years. And that's something that gets me really excited, and that's holographic near-eye displays. So holography has been around for a long time, but it hasn't really become practical until very recently. And this is something that I'd like to share with you about. Holographic displays, you may have seen holograms in museums. Here's a video that I downloaded from YouTube from the MIT Museum. They used to have a pretty good collection of recorded holograms. These are analog holograms. They are optically recorded of physical objects that were physically present at the time of the recording. But what you can see is that a static hologram is kind of like a photographic emulsion that encodes the amplitude and phase of the wavefront at the time of recording. And it has the ability to create high-resolution images over a large field of view with an incredible depth range also. It's really difficult to distinguish between a well-recorded hologram and a physical object. So holograms clearly have the potential to reproduce physical reality in a way that's indistinguishable for a human user. But we need to do this in a digital and interactive way. So what hinders us, or what's been hindering us for the last 60 years since this technology has been around to do that? Well, there's a couple of challenges. The first one is we need spatial light modulators, so small displays that can control the phase of light rather than the amplitude or the intensity. But these have also been available. So when you think about a holographic display that is meant for VR, AR purposes, it would look something like this. You have a laser on the left, like a coherent light source, maybe some collimating optics that creates a collimated beam. That beam illuminates this phase SLM, the spatial light modulator, which delays the phase of the light in a per pixel controllable manner. And so now the aberrated wavefront continues to propagate. And what you basically see is the interference pattern that's created by interference and diffraction in front of the SLM. So, each pixel of the SLM contributes to each point that you actually see. And you need an eyepiece or magnifying glass, basically, to see this because these SLMs are very small. But that's ideally suited for VR and AR because this is exactly the architecture of a VR AR display. So holography or digital holograms have the ability to create full three-dimensional images that you can freely accommodate in, and that hopefully at some stage, are indistinguishable from the physical reality. But why are they not physically indistinguishable today? Well, because we don't have great algorithms to compute the phase patterns on these SLMs for some target content. It's a computational display problem, really. And one of the big challenges is that the image quality of holograms, digital holograms, has been low. They can in no way compete with, modern LCD, OLED, or other display technologies in terms of image quality. And one of the challenges, probably the biggest, is this mismatch between the models that we use for simulating the wave propagation inside the display and what actually happens in physics. So there's a model mismatch, a sim to real gap, if you want. And this has been a core focus of our group for the last couple of years. And this is where we developed a set of techniques that we kind of call neural holography, where we try to combine the best of physical optics and traditional models and modern AI techniques. So I'll just give you, this is a series of papers, and I'll just give you the basic idea in a nutshell is that we use a camera that can focus at multiple distances, and we capture many pairs of phase patterns that we show on the SLM and intensity images that we record at multiple different depths. This allows us to, train a model that is parameterized by convolutional neural networks, and train the model to model the physical wave propagation that actually happens in the physical optics. And so we don't do this in a black box way. We actually combine traditional simulated models like the angular spectrum method, or ASM, and we only learn the difference between the simulated model and what actually happens in physics. So intuitively, why are the physics different from the simulated model? Well, there are optical aberrations, there are impurities of the source beam, there is electronic challenges in the SLM where you modify one pixel, but the neighboring pixels are also affected. It's actually very challenging to just calibrate this display. And you can think about this neural holography approach where we train this camera calibrated wave propagation model in an automatic way. It's an automatic calibration technique, really. And it gives us a differentiable model that models the wave propagation from phase SLM to any plane in this space in front of it. So this is a pre-processing step that needs to be done once. And then during runtime, we can take arbitrary input content, such as a 2D image, an RGBD image, a 3D focal stack, or 4D light field, and then supervise this pre-trained model in a way that allows us to estimate the phase pattern from our target content. And hopefully that bridges this gap between sim to real. In the lab, we mainly work on benchtop setups, so they're fairly bulky at this stage, but they show the promise and are starting to be miniaturized as well. So here's a typical benchtop setup for holographic display. There's a laser that's pretty small. It basically has 3 laser diodes, RGB diodes, that are optically combined and coupled into this optical fiber. The fiber brings the light to this, it's just a lens basically that collimates this beam. Here's the SLM, that's a off-the-shelf liquid crystalline silicon phase SLM that we typically use. And then there's a little bit of additional optics that do some optical filtering to clean up the beam. At the end, there's a camera capturing the content, and it can be focused at multiple different depths. So it looks pretty big, but there are clear ways to miniaturize this. We just haven't focused on that in the lab. In this case, I'm just using my cell phone to just peek into this port hole here, where you can see that there's actually an image being formed inside the display. And then, what you get with your traditional methods, traditional phase retrieval methods, like the old school Gershberg-Saxon method that was used to correct the initial Hubble telescope images, the images are noisy, and this noise is basically speckle. Speckle are random interferences of this coherent light that are very difficult to control. And in this case, one interesting thing that I want to point out is that the image is only constrained within the white box. This is from Big Buck Bunny. You've probably seen this movie. But a hologram cannot block any light. You can only redirect the light. So, for any excess light, it needs to redirect it outside the predefined area. So you'll sometimes see funny patterns around the boundary because they're not constrained. And the hologram needs to be able to do that. But typically, it would just block those out. So in 2020, we published our first paper at SIGGRAPH Asia on neural holography, and this idea of calibrating a wave propagation model worked out really well. And we were able to get clips like that. At the time, people were in the physical optics community were really excited about this. This is just a 2D video being played as a hologram, but at the time it was the highest quality RGB hologram that was ever captured, and people were jumping up and down and just adopting these AI techniques for real-time hologram computation. More recently, we've been focusing more on improving these models and also getting 3D results. So at this year's SIGGRAPH, we're actually presenting a paper that's called time multiplex neural holography. So here we use emerging MEMS-based phase spatial light modulators. We have new algorithms, better models. Here are a couple of examples. These are captured results, experimentally captured results of holograms that we capture with our prototype. They look very close to what you may be getting with a traditional amplitude SLM. And keep in mind that we show these phase patterns on the actual SLM, right? They're not really that interpretable because they only modulate the phase. But then what we capture at a slight offset in front of the SLM are these intensity patterns with the camera. And these are all experimentally captured results. I have a great team of students and postdocs who've been working on this. This is not done in real time. This takes a couple of minutes to compute per frame, so it's all pre-computed. But what I'm trying to say is that, if we just look at these results, they get close to amplitude SLMs, LCOS LCDs. But we can do this with a single pattern on the phase SLM or with multiple time multiplex patterns. There's no mechanical movements, no focus tunable lenses. So this is really interesting. And we're close to bridging this gap in the image quality between holographic displays and conventional displays. But there are other benefits of holograms. For example, in 2020, Facebook, and now Meta described a very thin pancake optic design that uses holographic lenses, which enables to make the form factors thinner, for example. So these use holographic optics. And this year at SIGGRAPH, in collaboration with NVIDIA and Jong-Yoon Kim, we are also showing at SIGGRAPH another VR display design that uses phase SLMs together with a waveguide to enable an ultra-thin VR display that is really in the form factor of eyeglasses. And if you're interested in that, I'll refer you to that paper. But the basic idea is that we can use these phase SLMs and holograms not just to create 3D images, but also to enable entirely new display systems that minimize the form factor compared to existing VR AR displays. They can also be more light efficient because they can reallocate the light. They don't have to block it. They can just reallocate it to regions where they're needed. We can do things like prescription correction, like myopia, hyperopia, but also astigmatism, higher orders. We can do all of that in software. We can correct optical aberrations of the optics and so on and so forth. So this is a really exciting area. And I think it's part of the future of AR and VR displays. Maybe still 5 to 10 years out, I would say. But really interesting direction that is really algorithms driven at the core, which is what makes it exciting for us. Okay, let's move on to some perceptually driven rendering. I think this is something that a topic that some of you have been working on, maybe more so than on the display and physical optics side. So I already showed you this illustration of the human eye, and I'm sure you've seen this a million times. But you've probably thought about, okay, what happens in the refraction, what happens with the photoreceptors, but I want to draw your attention to eye movements again. So when the eye moves, for example, by us just changing our gaze direction, then it rotates. But one interesting aspect that you may or may not be familiar with is that the center of rotation of the human eye, here denoted as C, is actually different from the center of projection. And when I mean center of projection, I think most of you will know what I mean. If you model the eye as a pinhole camera, then it's basically where that pinhole camera sits, or you can call it the no parallax point if you want. But this nodal point N has an offset from the center of rotation. And what that means is that as the eye moves around to gaze at different points of the scene, there's actually some amount of motion, lateral motion of the of this nodal point, of the no parallax point, or the center of projection. And what that implies is that there's a tiny amount of parallax that is induced by ocular movements. And now you may think, okay, this is totally negligible. I have never seen this in my own eye. But that's a really great question, and that's what we start out with. Is this effect even noticeable? Is it noticeable in VR? And can we dial it into the rendering part if we had eye tracking to improve something? So it turns out that this effect actually in the vision science community is known as ocular parallax. It's this tiny amount of parallax that happens as the eye shifts, and it is enhanced on the right here for rendering. As the eye moves left and right, you get this depth-dependent image shift, which is basically parallax. But it's small, and this is you have this variable resolution over the eye, where the fovea is actually only higher resolution, and in the periphery the resolution is lower, the visual acuity. So it's not clear if you even see this effect. If you dial it into VR in a VR system, which is what we did with I think this was an HTC Vive Eye, which has a Tobii eye tracker, then it kind of looks something like this. So here's a conventional rendering where we track the user's eye. You can see the gaze point in red, but nothing changes as the gaze moves around, right? But if you enable ocular parallax, what you'd see is that there's this tiny amount of image shift in these stereoscopic images that corresponds to the gaze direction. And I just want to say again that what we're looking at here is a rendering of the image that is covering a very large field of view for the user. So even though the movements look fairly large on the right, in the peripheral regions, those actually have a very low spatial acuity. So they're the user perceives them as being very blurred because they only actually look at the fovea on the right? So we did a whole bunch of user studies, and I'll spare you the technical details, but the basic answers we found is that this ocular parallax is actually visible in modern VR displays that have enough resolution. Something on the order of 5 arc minutes is already good enough. That's still far away from retinal resolution, so it'll become more prominent as the resolution grows. And importantly, the effect size is the same as what we see for retinal blur. So retinal blur is this out of focus behavior, which people have studied in the context of the vergence accommodation conflict and other things. And it's really interesting that this ocular parallax actually is very visible. Does ocular parallax increase perceptual realism if you render it in? Yes, it can if the eye tracker is good. It's actually interesting that there is a lot of redundancy built into the human visual system. So even if there's some amount of latency, you'll perceive it, but it can still increase the perceptual realism. It is actually an interesting effect. What we studied in a follow-up paper was an indirect implication of this ocular parallax, which is that it impacts the interpupillary distance. So now, if I asked any one of you what your interpupillary distance is, many of you would probably know it because we're all geeks and we love VR and stereoscopic displays. So on average, the interpupillary distance is something like 64 millimeters, and it's typically fixed. You dial it into your headset optically and also in rendering. But what this ocular parallax effect implies is that as you verge at different depths, so if you look at an object that's closer, your eyes will converge. The centers of perspective will actually move towards each other, and the effective IPD changes. It actually depends on your gaze depth, and it changes dynamically. So again, the question is, okay, does it actually matter if my IPD is a couple millimeters smaller or larger? Well, if you run some simulations and you simulate the distortions of the disparities, which will only happen mostly in the periphery, because at the gaze point, the disparity is typically 0, then you'll see that there is actually quite a bit of distortion going on. The question again is, do you see that distortion? Does it affect your perceived depth? And again, we ran a whole bunch of user studies, both in VR and in AR, and there's a lot of going on in the slide, so I'll just walk you through it. On the left, we did some experiments in VR where we showed specific patterns to users, and we measured the distortion of their depth perception. And turns out that for objects that are close by, the distortion is very noticeable. And this gaze contingent stereo rendering that you can dial in, basically dynamically adjusting the IPD based on your gaze depth, has a big effect, a statistically significant effect. For objects that are farther away, it doesn't really matter that much because the amount of parallax or depth distortion you'll see is small. So we found the same thing actually in AR, and there's again a lot going on, but I'll just point you to this plot here on the left. So for objects that are close, if you have a rendered stimulus next to a physical target, you'll get better consistency between these two across multiple different depths. So the depth will match between the two better if you dial in this ocular parallax rendering. It only matters really for objects that are close by. Again, for objects that are farther away, you don't really see a big difference. But what this means is if you want to build an AR experience where physical and digital objects are overlaid, and the digital object is supposed to be, let's say you have a little Super Mario that's jumping on your SIGGRAPH mug or something. If Super Mario is supposed to sit really on the mug, you have to get the depth just right. Otherwise, they'll appear to float somewhere else at a different depth. And in order to do that at close distances, you actually have to consider this gaze contingent stereo rendering. There are other effects like optical distortions and other things that you also need to consider, but ocular parallax is interesting and actually has a big effect. Okay, so many of the techniques I've been telling you about on the display side or on this rendering side require eye tracking. And I mentioned that eye tracking is something that seems to be solved already, but is not really solved actually. And we have looked into a couple of different directions, some modern approaches to eye tracking. I mean, then you would think, okay, we're just using neural networks, but no, there's actually a really elegant hardware solution to do eye tracking more robustly and at lower latency. Before I dive into this, let me just give you a general outline of eye tracking today. So today we have wearable eye tracking systems or near eye systems. These could come from companies like Tobii. You can buy these. Tobii is supposedly being used in the PSVR 2 also that's upcoming. It's being used in a couple of commercial headsets that are starting to come out now with eye tracking. So Tobii is like one of the biggest solutions here. Pupil Labs is a small open source company that have been selling these eye trackers for a while. And both of these types of systems run at maybe 120 hertz up to 200 hertz, I would say. They're not very power efficient. So they're mostly coupled with VR systems that are tethered or that have a big battery pack on the back of your head. And they have accuracies somewhere in the order of 0.5 to 1 degree, which is, I would say, standard for eye trackers. On the other hand, if you talk to your colleagues who work on vision science and who are in the psychology department and who do human experiments there, they typically don't use these types of systems. They use things like iLink. The iLink is like a dedicated desktop, desk-mounted eye tracker that costs you like something like $30,000 or so, and runs at like maybe 1,000, maybe 2,000 hertz. It's really fast. It's really accurate. People are typically strapped into these, chin rests, or maybe even have to go into a bite bar so they don't move their heads. The accuracy is not much better than these near eye systems, but it's just a lot faster. So what is the speed? Why does it matter? Well, if you want to do things like gaze contingent rendering, maybe redirected walking, or foveated rendering, foveated compression, every millisecond that you can save on the latency will give you a huge benefit on the bandwidth. So it's actually really important to have this speed. But how fast does the human eye actually move? Well, I mean, it does move quite fast. Microsaccades reach up to 200 degrees per second. So the most subtle eye movements are actually pretty fast, and going up to 200, 300, 500 hertz makes perfect sense. Up to 1,000 hertz, you probably don't need a lot more than 1,000 hertz to capture most of the microsaccades. But I mean, if you want to get all these details, then you need to have a fast system. So in a paper that we published, when was it? 2 years ago now, we played it through, like, what if we want the absolute fastest eye tracking system that's out there, maybe thinking about like 10,000 frames per second or something like that, like to make sure that we really capture all the fastest movements, maybe beyond what people even know, because we don't have any eye trackers that are faster than 1,000 hertz. So maybe there are movements out there that are faster than that. So if you wanted to have something like a 10,000 frames per second system, and you capture images with 300 by 300 pixels that cover, a reasonably large region around your eye, and each pixel is 8 bits, well, that's a bandwidth of 7.2 gigabits per second that you need to read out, just the raw data, before you even have to process it. And if you look at this logarithmic chart here, where the green line is USB 3, I mean, we can't even use USB communication protocols to read off this data because it exceeds the bandwidth of that. So the iLink with 1,000 frames per second is somewhere around here. Tobii is here. It comes with a huge bandwidth, and bandwidth is not only problematic in terms of like its systems engineering, but it also requires a lot of power. And power is probably the one big thing that doesn't work for AR, because it all needs to fit into the frames of your eyeglasses. Isn't there something more clever that we could do? Well, one insight that we had was that in a near eye tracking system, the camera is mostly mounted close to your head. And supposedly it doesn't move much with respect to your head. I mean, there's going to be some slippage, but maybe not too much. And what that means is, if we look at an intensity image, like the left one here, where the eye moves around, the only thing that really moves is the pupil and maybe the eyelashes when there's a blink. So this data isn't really sparse at all. You still need to read it out. But if you look at the temporal difference between successive frames, this is actually sparse because most of the image does move. Isn't there some clever way to exploit this insight that, most of the things that move are just the pupil and maybe the eyelashes in this case, to reduce the bandwidth and the speed? And yes, there is, and it's called an event sensor. Event sensors are cameras that are regular CMOS sensors, but they have an integrated circuit in each pixel that only reports the difference, the temporal difference. It basically reports an event per pixel with its XY location and polarity whenever the temporal gradient of a pixel exceeds a certain threshold. And that is perfectly suited for this eye tracking solution, because what that means is if we look at the same video that we just looked at now, is there's going to be a bunch of spurious events, but most of the events that we're actually recording are on the moving pupil and maybe on the eyelashes and so on and so forth. But most of the rest of the image is just blank. So we don't ever have to read out that data. This is an asynchronous thing, and the events are generated as they happen. So this isn't being read out at a fixed frame rate. And it doesn't have a fixed bandwidth. It's basically the events are just generated asynchronously and streamed off the chip. This is very power efficient and it's very fast. But it only works well for sparse scenarios. So now the interesting thing is that there are some event cameras that actually are hybrid. They can read out frames, conventional intensity frames, at something like 30 frames per second or 60 frames per second. And then they can read out events in between these frames. So these are actually really interesting. And we built on one of these Davis sensors. You can see the data that comes off that sensor here. So this axis is time. We basically read out fixed frames in a certain frame rate, but then we get these events in between. So this gives us kind of the best of both worlds. We get the frames, we can run traditional eye tracking algorithms, localize the pupil, maybe the glints, and then we can use the frames in between to update that position in between the frames. We did this using an online least squares fit initially. So we do traditional, pupil fitting on the frames. We use the events, do an online least squares update on the updated model that includes the pupil, the glint, and maybe here the eyelid also. From that, we can determine the gaze point also. So that's indexing into a pixel of a camera or into the display. And that allows us to get almost continuous eye movements. You can see that here, the fitted pupil, we're going to stretch out the time and compress it a little bit. You can see that basically you get these nonlinear behaviors and motions in between the frames, even at this really fast frame rates, up to 10,000 frames per second. Now, is it useful to do 10,000 frames per second? I'm not saying it is, but we wanted to push the boundary and the frontier of the latency and the speed with this specific paper. Here's a demo that we put together where we have one of these eye tracking cameras in front of the user, and they're just following the mouse pointer. So you can see that, it works pretty well. There's some latency from the USB protocols and so on here, but this is generally very cool. Actually works. One of my former students, Amit, is doing this little test here. And we also even had a small event sensor that is sort of wearable. It's not really at the size of what you need for an AR/VR system, but it is getting closer, and these event sensors are getting smaller and smaller. So this is a really interesting direction, and we're actively pursuing that, and I'll tell you a little bit more about this later. But the thing is, I'm just speaking for myself now, but I think I'm speaking sort of for all of us, is that we love technology. We love to work on algorithms. We love to work on other types of technology, but general people don't really care about technologies that much. They need experiences. They need cool things that they can do, really useful experiences that help them adopt this technology. So if we want this to be commercially successful, we can't just build technology for the sake of building technology. We need to engineer experiences. And this is where we need to think about what these systems actually do. And a couple of aspects of XR that I love include the following. Basically, augmented human performance. If you think about the single most successful wearable at this stage is actually eyeglasses. It doesn't do anything. It's just dumb. It has a pair of lenses in there and corrects your vision, but it's so useful that we wear it every day because it helps us see better. So this is just a pair of eyeglasses from Warby Parker. There are other emerging smart glasses that follow similar lines of thought. For example, Bose and others have these integrated sound systems here, so you can still use this as sunglasses or just regular prescription glasses, but they give you great sound as well. So you can take a phone call, you can listen to music, you don't bother your neighbor. It augments your hearing, basically. Or these Snap spectacles. Ray-Ban Stories have these cameras on there. You can snap a pic anytime. And so to some extent, they augment your memory because they allow you to capture photos in a more natural way than pulling out your cell phone or your SLR camera and taking a photo. So I think these are really great directions. I don't want to talk about augmented hearing and memory more, but I want to talk a little bit about augmented vision and eyeglasses because it relates to accommodation and focus, which I already touched upon earlier. And it's something that we can all relate to some extent. So normally we talk about people with normal vision. So what does that actually mean? So normal vision means that you're young, your lens in the eye can accommodate, it can change its diameter. You can accommodate between a near distance and a far distance. Again, the accommodation mechanism is kind of like a pouch filled with a liquid lens that's being deformed by these ciliary muscles and the zonular fibers that connect them to the lens. But many of us are nearsighted or farsighted. And what that means is that our accommodation range is shifted forward or back. So I'm nearsighted, for example, so I can see my screen well, but I can't see the distance well. So I need to wear prescription glasses to shift this accommodation range back into the normal range so that I can see distant objects. But farsighted people can see the distance well, but not near. So they need to wear fixed focal lenses to shift it back. And fixed focus lenses are great to correct nearsightedness and farsightedness. There isn't really anything we need to improve on this. However, as we get older, we will develop presbyopia. Everybody does, starts maybe around 45, 50, and is going to hit us all by the age of 60 or so. And what that means, presbyopia is a condition where you build up a protein in the eye, in the lens, that makes it stiff. It cannot be deformed anymore. And what it means is that your accommodation range is very short. You can only accommodate to one distance. It can be combined with nearsightedness and farsightedness, but the basic gist is that you can't see objects at multiple depths in focus easily. So for a normal person, for a person with normal vision, you can look at an object far away or close by. There's this autofocus mechanism of your eye that just adjusts. For presbyope, so somebody who's older, they can maybe see far well, but they cannot ever read anything. So what they need to do is they need to wear reading glasses, and reading glasses work well. They can shift our accommodation forward, and you can read well, but then you can't see the distance. So reading glasses only shift the focus to one specific depth, and that's challenging because you need to put them on and off. You need to, maybe you forget them, while you're driving. You can't simultaneously look at your dashboard and the traffic. So this is where progressive glasses come in. Probably one of the most popular correction methods for presbyopia today. Progressive glasses have a varying focal power over the vertical region of the lens. So on the top part, you can see far. On the bottom part, you can see close, kind of the same as bifocals. The problem with progressives is that the field of view for any one distance is severely reduced. So you actually only have a small corridor on the top of your eyeglasses through which you can see the distance, and a small corridor through which you can see the close distance. So you kind of have to use your head to align it with whatever distance the object is that you're fixating. And so progressives have problems. The natural solution is to just look at an object and the object coming into focus automatically. So, can we build some technology that kind of solves that natural, brings back this natural accommodation behavior? Well, the answer is yes, but we need dynamically focusable glass lenses in this eyeglasses pair. And there's a couple of options of doing that. There are physically movable lenses that are called Alvarez lenses. They're two pairs of lenses shaped in a way that creates a lens with a specific focal power where the focal power shifts. We can use liquid lenses that are basically operates like the lens in the eye. You can apply some pressure here on the side, for example, using piezoelectric motors that deform the shape of the membrane to focus at different depths. And there are also emerging liquid crystal technologies that are kind of similar to LCDs, but that just change the refractive index of the material dynamically. So there's a couple of different options of dynamically changing the focal power of a lens. And the question is, is this really useful? Does that make sense? Does it actually improve people's vision? So we started prototyping with some of these ideas. Here's an early prototype. It looks more like a pair of ski goggles. We used large liquid lenses. We used a stereoscopic eye tracker from Pupil Labs. In this specific prototype, we had a depth camera on there from Intel also. So large focus tunable lenses, they're kind of affected by gravity because they're liquid. So, we need to have some correction mechanism for that. So this is more like a research grade prototype. This is not something you'd actually use. The important thing is you also need to be able to correct for myopia, hyperopia by putting fixed focal lenses in the front. So we call this autofocals because it's an autofocal mechanism. And what it does is basically you track both eyes. You estimate the gaze depth by estimating the divergence angle between the gaze directions of the two eyes. And if you look at an object that's close by, your focus lens is close. If you look at an object that's far away, like this RenderMan teapot here, the box and the teapot is close, the box is far, depending on what you're looking at, the lenses will automatically adjust the focus. And you get the full field of view, right, at this focus. There's some aberrations here on the side which come from the eye relief between the camera and the lenses. If you actually put it on your head, you don't see that much. Okay, so we ran lots of user studies. We showed this at eTech also, actually in 2018. Tested a lot of people there. And we found that it significantly improves the visual acuity over multiple depths compared to monovision and some prescription methods. But it importantly improves the task performance over progressives also, because you can basically look at small objects at different depths using your gaze only. Whereas for progressives, you have to always align your head, and that takes time, and it's not as efficient and not as natural. So even people who typically wear progressive glasses, we were able to improve their task performance in visual tasks using this first autofocus prototype. So this is a really great idea, I think, to help people see better. It doesn't use a display at all. And this is a slightly different paradigm from, I think, how most XR companies think about VR and AR today. Typically, we start with a big display that has all the different features that we want. And then over time, we try to miniaturize it, make it smaller and smaller. So these are some examples here, right? And we hope at the end of the day, we have something that's small and has all the features in it. But I think another way to think about it is we just start from eyeglasses because they're so useful as is already. And we just add the most useful features to them, maintaining the style and the form factor of the eyeglasses. So we could add some sound features. We could add some vision correction or, help people see better. And eventually we can maybe add a display, because smart glasses are more than just the display. And I think the form factor, size, and power constraints are more important for people than, some of these systems, because I'm having a hard time imagining people running around on the street with these types of systems. So one startup I co-founded with some of my former students is called Zin Labs. And in that context, we are actually developing all-day wearable eye tracking that is super robust and super low power. So I'd be more than happy to chat with you if you're interested in this technology. So it's coming. It'll take a little while, but we're going to have very fast, super low power, absolutely robust eye tracking in these tiny form factors soon. Okay, that concludes my talk. I told you a little bit about some of the recent projects that we've been working on AR, VR, and wearable computing in general. My lab is actually the computational imaging lab, so we work on a couple of different topics, including computational cameras, single photon imaging, using AI to redefine applied optics. We work on computational microscopy, neural rendering. These are all other topics that I didn't have time to touch upon today, but lots of really exciting things happening. And I hope this was interesting and informative to some of you. There are lots of challenges on high performance graphics in this space of systems engineering or display systems engineering. I'd like to thank all my students and postdocs, current and former, and also our sponsors. Hopefully we have a couple minutes for questions. And thanks again for the organizers for inviting me. This has been a pleasure to be part of this conference.
Thank you so much, Carsten, for a wonderful talk. It's amazing to listen to you each time, and thanks yet again for showing us the technologies that will drive the entire stack of future XR. This is amazing. We actually have quite a bit of time for questions, like 10 minutes. And while people are either typing it up or stepping up to the mic, I have quite a few questions for you. These are some of my favorite topics as well. So I'll start with eye tracking. Like you, I've also been frustrated at the pace at which the technology has evolved and improved to become usable in VR. And one thing I found while I was working with, at least with foveated rendering, was that the end-to-end latency of the system tends to be dominated by the non-eye tracking parts, namely the display, at least in the VR applications. And I always kept worrying that even if I had an infinitely fast eye tracker, I would still have like 30 milliseconds before I can show something based on the tracking. So do you feel like the display technology needs to evolve in some way in tandem with, or maybe even the algorithm should be involved in
Absolutely.
tandem with eye tracking?
Yeah, this is such a great point. So, and this is what I tell my students in the class on VR that I teach is like VR and AR is a systems challenge. Like it's always limited by, the bottleneck may be somewhere. Whatever the weakest link is, this is how good your system will be. And that's why it's so important to consider all of these aspects. And those include rendering, hardware acceleration, displays, but also the human eye and the camera system. Everything has to work together, right? That being said, like conventional cameras, have lots of latency and lots of power actually. So I think these event sensors are mainly useful for bringing down the power, right? That this is mainly the main benefit. Yes, they are also fast and they're also robust. So these are great additional benefits, but I think it's mainly there for power. But it's hard to give an exciting talk about power saving. So I didn't really emphasize that aspect. But you're right. So let's think about the display. There are many different displays that are actually being used today. So, LCD is maybe the dominant technology for most monitors. We don't really use it for VR that much, but in an LCD display, you have a fixed frame rate, maybe 60 hertz or something like that. But the image is actually being scanned out sequentially over the LCD panel, and there's no way for you to change a pixel until your write out mechanism comes back. Maybe NVIDIA has a couple of tricks up their sleeve, obviously, but it's actually challenging. OLEDs can be fast and have low persistence, so they can actually drive pretty fast, and they're really useful for VR. But there, the limiting factor will be the backplane. The backplane and the electronics that are actually driving the OLEDs, they will be the limiting factor because they're going to have to minimize the bandwidth, otherwise the power goes up, and you need to have smart backplanes. And that is a key requirement for, I would say, VR. And some people have been working on this. So, for example, Compound Photonics has publicly talked about for a couple of years about their smart backplanes. And what that means is that you can directly dial in the eye tracking location, for example, the gaze position into the backplane, and you have not just a foveated rendering mechanism, but a foveated backplane if you want. So you can, directly turn on at a high resolution the backplane, but you have to synchronize it with the GPU. So everything has to be done in harmony. Now, OLEDs aren't really all that useful for AR because in AR you have a waveguide, and the waveguide is so optically inefficient that you only get about 1% of the light coming out on the other end. And an OLED is limited in the peak brightness that it can do. So there we need micro LEDs, and this is something that we've worked on at Raxium, and other companies obviously are working on this. But there again, the limiting factor is going to be the backplane. So we need backplanes that support that. And then thinking about laser beam scanning, so lots of developments on AR or out there at all the big fan companies, obviously, and some of them are thinking about using laser beam scanning, and laser beam scanning is basically using a waveguide that's very thin, using a little MEMS mirror that scans the laser basically point by point, like raster scanning the point, like your good old CRT monitor. The thing is, again, like if it's a sequentially scanned display, there isn't anything you can do in terms of saving the latency, right? It's not like you can steer this laser to arbitrary positions. It's not like a vector display. It has a fixed oscillation rate, this mirror, right? So different display technologies are differently amenable for reducing latency. And again, it's a systems challenge that includes many factors, including form factor, power, latency, and many others. So there's so many different components that have to come together and all work in harmony that, it's challenging. Sorry for just babbling on here in your simple question. I think it is a complicated issue is what I'm saying. And all these components have to work together. Yeah.
I think
it's the key question.
Yeah, definitely. So there are a couple more questions on the board. I think the first one was, Canon seemed to have very mixed results with the eye tracking for autofocus point in the R3, according to reviewers. How much difficulty do you expect in getting a robust solution in the field?
Sorry, can you?
So Andrew, is it possible for you to elaborate your question? I don't know what you what you mean. Well, while he might step up to the mic, let's me talk about the next question. It says,
okay, I mean, I think
okay.
I know what you're talking about, but
Okay.
when you think about eye tracking, there's a couple of different aspects to it, right? Like if you think about a single eye, typically, first of all, we want to estimate the pupil and maybe the glints. From that, we get a model, we get the gaze direction. And so indexing from the eye tracker into the pixel of a display is a challenge because you need to be robust for slippage and so on and so forth. But I think what he's saying with autofocus point is like binocular eye tracking is also, you need to track the gaze direction of both eyes and then triangulate it and get the vergence angle between them, right? That's actually very challenging because, what we said earlier is like you have a accuracy of like 0.5 to 1 degrees maybe for each eye, which means that there's actually quite a bit of wiggle room for each eye, and getting the gaze angle or gaze depth robustly is challenging. Yeah. Is that what you're referring to, Andrew? Or
they might do better if they use both eyes. No, I really just meant, so Canon used to have some old film technology where they tried to estimate where the eye was looking in the frame and use that to select between their options of autofocus points. And they've resurrected that recently for the R3. And some reviewers are saying this is wonderful. It's the most interactive automatic way of deciding where to focus in the frame. It's completely going to revolutionize things. And quite a lot of other reviewers are saying it doesn't work. I can't get it to work. You have to calibrate every 5 minutes. So I'm just wondering how.
Calibration is challenging, right? Slippage. I mean, you can typically, the way these eye trackers are calibrated is you have this 9-point calibration method that is happening per user, per use case, right? You show 9 points. You build some kind of a lookup table, and then you assume that the eye doesn't move with respect to the screen, and you can track the gaze, right? It's unrealistic because if you have a wearable system, there's going to be some slippage. If you have a monitor, you have to keep the head fixed. That's why people in these vision science communities use headrests to keep the head stable, or even bite bars where you have to bite on something just so that your skull doesn't move. So, building something that's robust to slippage that's challenging and sort of independent challenge from everything I've talked about. It is a big challenge, but I can't say it works or it doesn't work. There is a lot of smartness going into that, and I'm sure we'll see good things happening very soon. Like if you can get gaze, so glints and pupil separately, for example, there's some robustness built in, and there's a lot of interesting ideas out there. But yeah, I would say it's possible, but it's very challenging, actually.
Yeah, cool. I look forward to seeing the crossover of research anyway. Thank you. Cool talk.
Next question, I think it's also a systems-y question. Thanks for the talk. Some perceptual effects, the ones that you described, some of us will never think of and require a lot of research and knowledge, just to research and various different science domains knowledge. Do you think every engineer working in this space would need to be familiar with those, or is there a way to decouple it from such systems software design perspective?
I mean, yes, again, like AR VR is a systems challenge, but so is computer graphics, right? Like if I remember my first computer graphic classes many years ago, too many years ago, I mean, we learn about human vision, about color perception, about radiometry, about physics. There's many different components to it, and it sort of became a thing in graphics where we have pretty standardized courses that we can take as undergrads to help us understand at least Vision Science 101 from a very high level perspective. And it doesn't mean every software engineer has to become a vision scientist, but I think it's good to understand that, the fovea has more photoreceptors than the periphery, and that there's some drop off. And I think, that we have 4 different photoreceptors in our retina. So it gives us like trinocular vision or day and night vision. So very simple concepts from vision science, I think, are not only exciting, at least to me and to many of you also, but also something that I think people should know about, but it's a different level of abstraction. That doesn't mean you have to be a vision scientist to do that. But I think, again, XR is a systems level challenge, and be able to at least understand the basic concepts at a certain level of abstraction is required to really push it forward. Maybe not at every level of an engineer, but if you really want to push the needle, you need to consider multiple different areas, and working in interdisciplinary teams, at least, is sort of important, I think.
Perhaps there's also opportunity for sort of computational models or systems that are like, intermediate black boxes for one community to use from the other, to sort of
absolutely
unblock each other.
I mean, if you think about what vision science does as a field, is they build models, right? it's actually a really boring field if you think about it. Once you have a hypothesis, you have to run many, many user studies, capture lots of data points, fit some model to it. And that's what vision scientists publish. And then, we're sort of it's beneficial for us because we can just take that model and then apply it and build really cool rendering and display technology around it. And I mean, some of us also more on the vision science side, or at least try that a little bit. And I think some of us get more excited about it, others get less excited about it. But I think the important thing is the interface between the fields. And these are typically these mathematical models that will model your, for the visual acuity over the retina and things like that. And I think, I teach these things in my VR class, and even the undergrads understand at least the basic concepts of that and play around with it a little bit. So I think that's about the level of abstraction that I think every engineer who works on XR at least should understand them. But again, you don't need to understand all the different types of cells or all the different nuances. I mean, this is beyond what I understand too. Like, I have a lot of colleagues here in vision science who, for example, like one interesting aspect is that the photoreceptors actually mechanically deform by a few nanometers whenever they fire or something. Is that important for graphics research? I don't know, but I have some colleagues who built interferometric measurement systems for the retina who study the mechanical deformation of photoreceptors when they fire. It's just interesting, but I don't understand it as well, right? Like, I think it's fine.
Fascinating.
Yeah.
There's one more question, and I think I have like 10 more questions, but I think we're running
Sure.
out of time, and we're eating into our break. So I'll take one more opportunity to thank Carsten for once again spending time with us and talking about all the awesome stuff we've been working on and what lies in the future. So thanks so much, Carsten.
Thanks for having me.
We will now have a short break for about 1 minute until the next talk. I encourage everyone to attend that. Meanwhile, please take the opportunity during this day to cast your votes for the best paper as well as best poster. The best paper vote button is like right above Gordon here, and then the best poster button would be in the posters room. So please make sure you do that and enjoy your break. See you in a few minutes. Thank you.
Hi, Noshaba. I think you might be muted. We cannot hear you.
Oh no! Oh, okay, I'm sorry. Thank you. Okay, I'm sorry. I was just saying that I want to welcome. So first off, I'm Noshaba Chima. I'm your chair today, and please give a welcome to Gabriela and Antonczyk. I'm sorry if I butchered your name. I hope, maybe you can. Yeah, I'm sorry. So she's a brand manager at Deutsche Telekom, where she's leading various international projects within the brand experience team. And most recently, she's been involved in the equal eSports initiative driven by the Deutsche Telekom, where together with some other partners, in especially in the eSports community, especially League of Legends, with SK Gaming and that sort. Yeah, so today she will talk about that initiative. So.
Yeah, super. Thank you very much for the great introduction, Noshaba. So yes, my surname was almost correctly pronounced. So it's Antonczyk. I'm from Poland, so it's a Polish surname. So yeah, thank you very much for having me on the HPG conference. I'm very happy to be part of the diversity and inclusion talk today. At last day, I think you are still awake there. So yeah, before I start, I would like to ask you a few questions in the audience, I would say. Yeah, think about this. Does your son play video games, or does your daughter play video games? Or let me put differently, what do you see in your close environment? Do you see more girls, women, or boys, men playing video games? So while you are thinking about possible answers, let me start with my talk, with my presentation about reaching the unreachables with our Equal Esports initiative at Deutsche Telekom. I would like to start with Brenda Laurel, which is a video game designer. So she used to work at many different companies, and she was actually surprised or shocked by the companies who didn't basically think about a female audience while developing and producing games. So basically, the usual answer was, well, of course, girls don't play games, so yeah, why to bother to develop the games for them? So, and she was shocked by this. She herself wanted to do something with this, so she co-founded Purple Moon company in US and started to do research about actually why girls don't play video games. Why there is no games for them, developed for them. So she started to look into this already back in the 90s. Yeah, we are a couple decades further, and actually the situation didn't change much. So if you look at the covers of video games, currently you still see a lot of male characters presented on the covers. So, but this is basically not the issue only in the gaming or esports industry. When we look actually back a few years in the back in the sport, into athletic world, also there women were struggling to position themselves, to have the right to play. So here as an example, Billie Jean King, former world #1 tennis players, she has been asked very often, if she is a woman or an athlete, which is really absurd, because men, they were not asked, or they are not asked this kind of questions. And of course she was both, right? So women in sport could somehow already path their way and could establish a better position and told the stories how to do it. And now is the time that women, girls write a story in esports and gaming scene. So if we look at the at the numbers, I have here a few numbers actually focusing on the Germany, because we, with the initiative, focusing currently mostly on the Germany. If you look at the numbers, if you look at the male casual gamers and female casual gamers, so here is the split really basically almost 50-50. So the message is, or how we could interpret it, is that the female gamers, they want to play and they are highly motivated. The motivations are different a little bit, right? So they want to express themselves, they like the fantasy world and experience the stories, but mostly also they like to accomplish something, so complete the games. So the motivation is theirs, and then there's a question that why, when we look a little bit further into esports enthusiasts, so people who are not only playing on the regular base but also are fascinated or engaged in the esports, then the split look already completely different. So here we see male esports enthusiasts like 90% and female esports enthusiasts 10%. And even looking a step further into competitive gaming, here you can compare here the graphs. The female percentage decrease into 5%. Some of the research are even saying that this is like 1%, or when we are contacted with our experts, it's like between 1-5%. So why this situation is happening, and what can we do about it? So these were the questions we had last year at Deutsche Telekom with the team which I worked with. So we said, like, we would like to support the women. So we would like to change the situation and enable women in the gaming world, especially on long term. So it's not something short right now, like campaign, is really initiative on long term, and elevate them into professional level. So we reach out to young female or non-binary gamers and try to create for them a safe space that they can develop themselves and get prepared for the esports competitive level. And on long term, we hope, so we are starting now with the smaller group with the female non-binary gamers, but on long term, of course, we hope that it will lead to establishment of mixed teams. We are not doing this alone. We couldn't manage to do this alone. So we have two strong partners on board. On one hand, as Noshaba already mentioned, SK Gaming. SK Gaming is leading esports company on the professional level. And with SK Gaming, we established female team in order to get them prepared on the competition on the highest level for the future. And on the other hand, with Esports Player Foundation, which is a non-profit organization, we created a special program for the talents which maybe are not yet there to get to the professional level, but we hope that with the in-game coaching session, with the proper workshops, with the training, they can get there. So the talents who are showing the potential, we are supporting them on long term with Esports Player Foundation. So this is the initiative with us as Deutsche Telekom. So we basically wanted to, together with partners, create this initiative to help women and non-binary out there to get their chance in the esports and gaming scene. And we've launched our initiative last year in September, and we could already celebrate last year some achievements, some success. So basically with SK Gaming, already last year we co-found female talent team Avarosa. And with Esports Player Foundation, we got 10 talents in our program. And with them, as I said, we did different workshops, fitness boot camps, and really to get them prepared for the professional level. Then on top of this, last year we had our first eSports festival in October in Berlin. So it was a very nice event with positive feedback throughout the press, throughout the media, social media, but also from the visitors, from the people on site who were very surprised by the positive and open atmosphere we created. We had people, we had players, we had our talents, we had Team Avarosa. There's so from esports and gaming scene, but even on top we had personalities from the esports and athlete worlds. We had mental and health coaches. We had also coaches for the parents. So the parents, they basically are aware that the esports scene is not maybe anything bad, and they can support their young girls to get there and basically to maybe have a career in the esports scene. So it was a very successful year for us. Even though we started actually in September, the initiative, and we won't stop. We didn't stop and we won't stop. So this year we started with directly with the bootcamps with our esports talents. You can see here some impressions on the slide. Moreover, we have our Equal Esports Council with very strong role models from esports gaming, but also business world, and they provide the support for the Female Talents program. Right now we are in the application phase together with SK Gaming and with Esports Player Foundation for the new talents, but also for the with the new game content. So beyond League of Legends, we started application for the mobile gaming, Brawl Stars. So here we are addressing even younger talents. And the feedback I was talking today with the team, the feedback is really positive. So we see even more applicants compared to last year. So the community is growing and we are very happy about this. And since last year festival was very successful, of course, this year we will have the second Equal Esports Festival in Cologne, this time in September. More details I cannot tell you right now, but if you check our website, which is included on the last slide, there we will be posting very soon some more details on this one. So that's it from my side, actually. I think we are good on time. We have few minutes now for any question you might have. If not, that's also not a problem. You can always find me on LinkedIn, ask questions there. And if you want to know a little bit more about the initiative, about what we are doing with the partners, we have also a very interesting blog articles on our equalesports.com website. So thank you very much from my side. And now I'm open for your question.
Hi, thank you for your nice talk. So how did this come together, like in the initiative?
Yes, that's a good question. So last year around April, May, we started our talks with the partners, with the SK Gaming and Esports Player Foundation. So we are, in general, as Deutsche Telekom, very engaged into social topics as well. also due to social responsibility, which we are driving, which is very also important for Deutsche Telekom. And actually, in the team of brands at Deutsche Telekom, there was a campaign which started way before Equal Esports Initiative about a hate speech. So, or actually against hate speech, anti-hate speech campaign in internet, online. So, because of course we are providers of internet, fixed line internet, mobile line, but also we have to we have the social responsibility, and we try to address that. Yes, everything what is happening online, it's not only always good, but there is also, as you probably know, a lot of hate speech out there. And we started a campaign before Equal Esports Initiative some time ago, and in Germany, and it got very positive feedback. So we were addressing the anti-hate speech, or what kind of impact hate speech can have on the people, and this somehow brought us also into esports and gaming environment. And because we are supporting the partners as the Gaming and Esports Player Foundation already for some time, we got in touch with them, and they made us aware very strongly about the issue, and about also the statistics, which are actually very terrifying when we look into competitive gaming, that the female gamers are really a low percentage compared to the male gamers. And we started together with the partners, because they are the experts, they have the expertise in this environment. Together with SK Gaming and Sports Player Foundation, we were really thinking long about the concept and about how to make this as telecom, because it's not maybe something which everyone is connecting esports and gaming directly to the telecom. So we were thinking long term how we can address this properly in the community, and this is how it started. Yes, I mean, the topic of equality and diversity also is nothing new for us in general. So the company Deutsche Telekom itself, we are also driving more for equality and diversity at our company itself. So it was nothing new, but now we try to together with the partners, we try to support the female gamers and make them their dreams come true and get into the professional level as well.
Okay. So Daniel's asking, here in Germany, I haven't heard from that before. Does Telekom plan to do more advertisement for it in television, social media, and posters?
Actually, yes, television not, but in social media a lot, like Telekom Talk, Telekom Erleben. So these are the channels in Germany, and of course the press releases. So, but that's to the point. So we still don't do enough since the people are not getting the message. So, but the website it's active, it's online, and there we are posting always all the news, and the application phase still is ongoing.
Mm-hmm. And so at HPG, we would like to have more diverse.
Hello.
Okay, so at HPG, we want to have more diversity as well, right? So how do you, I've heard from some people that, I mean, I'm not sure if you conducted this study or another institute or some, that people in general, no matter their gender, if they're male or female, if they've played a game, they're more likely to choose STEM fields. Did you conduct that study or?
No. So basically, the studies I used here, they are from market research. So basically, there were sources also written. So we didn't conduct the studies. No, okay. we are actually now, to be honest, are looking into our own research to get a little bit more information about the scene, because we basically got what is there available through our partners. Also interesting thing, I don't know if you know it, a lot of female gamers are actually on purpose choosing the male characters, and they basically hide their female names. So basically they go undercover in order not to get any hate speech in the game. So basically they are trying to cover their gender. So that's really terrifying. There was actually campaign a few years ago, I think 2018, 2019, in Brazil with Vivo, also with the telco provider, under my game, hashtag my name, my game. So, and it was just like a short campaign in order to make also people aware that that there are female gamers, but they are very often hiding their real name under male nickname. Hello, are you still there?
Yes. I think we still have some minutes, right? Okay, no, actually, no. The technical paper session should also start roughly by now. Are there any more questions, or good? I guess we can also go to the next session now. Thank you so much for your very nice talk.
Thank you much for having me.
Thanks, Gabriela. Thanks, Noshaba. Our next session is our last technical papers session on acceleration structures. I'm Dave McAllister. They roped me in to chair this session. I love this topic of acceleration structures. Our first paper today is Data Parallel Path Tracing with Object Hierarchies by Ingo Wald and Steve Parker, both from NVIDIA. So go ahead, Ingo.
Are we live?
I think we are.
Okay, sorry, there was some technical issues. Okay, welcome everybody to this talk about data parallel path tracing with object hierarchies, which is joint work together with Steve Parker. So in this talk, I'll be talking about interactive data parallel and GPU-enabled path tracing for Moana-like content. So what we're particularly interested in is models that are larger than any one GPU, in particular models like Moana. So production content with lots of instances, with lots of shading data and so on. And in particular also for full path tracing, so not sideways like rendering, but real full honest to God path tracing. So if you read the paper is actually online on arXiv already. If you read the paper, there's actually three different things that this paper talks about. The first one is a new paradigm regarding how to think about partitioning data in a distributed rendering content, like which node can have which data. In particular, we want to enable nodes to have content in a way that different nodes can overlap, that we can replicate certain things, that we can split them up, etc., in a much more general way than is possible with spatial partitioning, which everybody uses today. So that is the main important thing. Then the second thing it talks about is some algorithms that realize this kind of paradigm. And finally, you couldn't actually evaluate that without having a complete system that is using that with a wavefront path trace and MPI and all that kind of stuff. So there's a lot of stuff in the paper. I could easily talk an hour about each one of those, but with respect to time, I'm only talking about the first 1.5 of those, and even those only in a motivational session, because if I can't convince you that this entire concept makes sense, then the rest doesn't even make sense. So data parallel rendering. The concept of data parallel rendering is that you have multiple nodes that work together to render a certain image and a certain model. So every node only has a certain part of the model, usually because the model is too big to fit on one, so you want to split it up over multiple nodes. A node might mean a GPU, it might be a physical node in the cloud or something like that. The way you do that today, most of the time, is via sort last image compositing. That is a widely used technique in scientific visualization. It works great, it's fast and everything. The problem is that doesn't easily work for secondary rays. So for ray tracing and path tracing, it's not so useful, so that's not for us. So the alternative to that, if you want to be able to trace arbitrary rays or path or whatever you want to call it, and a ray on a certain node is being traced and needs content that is on a remote node, well, you have two options. You can either fetch the model data, BBH data, and whatever else it needs from the other node and then do it locally, or you take this ray and send it or forward it to the other node that has the data. That's basically the two choices that you have. And there's a lot of discussion in the paper of why we choose one over the other. I don't want to go into that here. Just saying for this particular paper, we're interested in the forwarding approach. So rays travel across different nodes until they find the hit point and shade where that data actually is. So in that context, in the ray forwarding context, there's two questions that you need to answer if you want to do it. The first one is, how do you want to partition the scene? Like, which node gets which parts of the model? And the second one is, if I have done this partitioning, how is a ray being traced across these nodes? Like, what nodes should a certain ray be sent to, which is the next node that every time a ray has to be forwarded, where is it being forwarded to? And there's actually two interesting observations if you start looking at that problem. The first one is there's not much work on that. There was a lot of that in the very early times when dinosaurs roamed the earth. But in the last 2 decades, we've pretty much talked about that on and off in forums like HPG, but there's not much work on it. The second observation is that pretty much every of the recent papers on data parallel rendering assumes spatial partitioning. And that has some issues, which I'll talk about. But let me first talk what I actually mean with spatial partitioning. Take this kind of scene, and you have a few instances of 3 different kinds of trees or palms, whatever, and a few other objects. And now you want to do some partitioning of that. You could do a spatial partitioning like this grid, could also be a KD tree, octree, doesn't matter. The outcome of that is different regions, which we call domains, that do not overlap. In each node, each rank gets one of these domains and all the geometry that overlaps that domain. That's a very, very simple thing to do. That's probably why everybody has done it. Now, if it's a spatial partitioning, that means that any object that overlaps multiple different domains, it actually has to be replicated in there. That's just the nature of spatial partitionings. We all know that. But again, that's easy. Also, if you want to trace array through that, it's easy. It's always very obvious which cells of this, which domains array has to traverse and which the next one is, and once it's done. So all of that is very easy, which is probably why everybody is using it. The caveat with that is that there's a lot of issues with spatial partitionings, which this community here over the last 1 or 2 decades has discussed. The community has mostly gone over to BBH-style partitioning, object-space partitioning for ray tracing. And there's a lot of issues that I don't want to go into. For our particular problem, the main issue is replication. So to explain what the issue actually is, let's have a look at the content that we actually want to render. So this here is a view, a top view of Moana on the top right. The full scene is actually larger because the ocean and the ocean floor are actually much larger than that. The white area is the beach that you see as the main shot cam, the main view that you want. That's where most of the instances for the trees and bushes and so on are. And if you zoom in on the beach, that's where you see all of the tiny instances where there's literally millions of those little twigs and pebbles and all over the place. So with that in mind, there's a few things I would like to point out for that kind of content. The first one is there's some meshes that span almost the entire model, like the ocean floor or the ocean surface or the beach or the mountain base meshes. They are gigantic compared to some of the instances. The other thing is that many of the things that have instances, they have instances scattered all over the model. Like there's certain trees that are on the left side of the island and the right island, and they're all over the place. And then in addition, in a rendering context, you typically do not want to split certain things, or it's not easy to do that. Like if you have an instance of something, you can't easily split it because all the other instances share this thing that is being shown. And also if you have meshes, even if they don't have instances, they might have additional shading data like baked textures in this example that makes it hard to split those things. So with that in mind, take this kind of content and spatial partitioning and do a little thought experiment and take this dumped down 2D, 1D, whatever example of Moana. So you have two base meshes, a rock and a mountain, the two green lines. And you have two types of trees, red and blue, and multiple instances of that. And let's do a spatial partitioning. So take something that's partitions into 3 ranks. I would claim that's actually pretty good partitioning. And you see right up front, it's very easy to trace array through that. Everything is easy. It's simple to do. All is good. Except if you look at what kind of meshes actually overlap each of these spatial domains, you'll see that every one of these ranks has 3 of the 4 meshes that it actually make up the entire scene. So if our idea of our goal was to reduce the number of meshes, the number of memory that each rank has, this was a total failure. It doesn't actually work that well. We wanted to have 1/3 of the meshes on each of these 3 ranks. What we end up is 3/4. So that was not very good. The second thing is, if you trace these rays through that I've shown here, these rays actually touch both rank 0 and rank 2, even though they're not even close to the geometry. And that means these rays have to be sent to these nodes, and that consumes bandwidth, and it's expensive. So it's not even good from a performance standpoint. So if spatial is bad, how would object space look? Now do something really dumb and take all of the red trees, put it on one rank, take the blue trees, put it on another rank, and take all the other geometry and put it on the 3rd rank. And then put some bounding boxes around it and do some magic, just hypothetically. The first things you realize is actually it's pretty good in terms of partitioning, because now every rank only has a very little amount of memory. So that is really good. But you have to somehow be able to traverse that. And that's not so easy. And in particular, if you just use these boxes for traversal, that would be horrible, because every rank would have to go to every ray would have to go to every rank. But if you look at some of the papers and techniques that we built for BVH construction in ray tracing in the last few years, in particular spatial splits and rebraiding, the idea there was that if you have large unsplittable objects or instances, you can represent them often with smaller and tighter boxes if you use multiple boxes. So let's do the same thing here and represent each of the meshes with multiple smaller boxes and reach into the objects and put a single box around each instance. And suddenly this would look much, much, much better. We still have the benefits from the object space partitioning, but the ray, if we had a clever traversal algorithm, in this case would not have to move at all. All the work could be done on the red node. So that is basically what we want to be able to achieve. Now with that, the question is, how can we actually do that? The first insight that we had is that we have to think a little bit harder about how we actually want to represent remote context or a distributed scene. And we do that in our paper in the final version with what we call proxies. A proxy is a region of space, basically a 3D bounding box, that contains something. That something could be a part of a mesh, it could be an entire mesh, it could be 50 instances. It's something. And it also contains a list of nodes, typically one, but could be multiple if we replicate certain stuff, which we can, that own this content. So every other node, if it comes to this box, knows there's something on this other node that we have to ask this other node about. So that is the basic representation that we use. Most naively, think of looking at each instance, assigning each instance to exactly one rank, and put bounding boxes around that. So take this scene, for example, 3 different types of trees. We sort them once again by object type. So all of the red ones go one rank, the green ones another, and the blue ones another. Now we could put a bounding box around each one of these instances, world space, and that would be a valid set of proxies. That's the easiest way to think about that. But it doesn't have to be this way. We could also say, in some cases, we might merge some of these instances into a single proxy, just to have less of these proxies around. Or we could do the opposite. If we have one that's just a giant box around this thing, like a base mesh, we can split it up into smaller ones and use multiple proxies to represent the same thing. And that is basically the power of this scheme, that if you know how to build it, and that of course is a challenge, then you can represent this really, really well. And the color of the boxes in this case basically encodes which nodes, which ranks have the data behind these boxes. Now, if you want to traverse that, the first idea that we had is we could just take all of these boxes. Every rank would get all of the boxes, even though they only have one content, and trace that through these boxes in a BVH-like way, maybe with a stack-free BVH traversal or something like that. So you would maybe first traverse the green one, then the red one, then the blue one, then the red one, etc. And that's kind of an obvious way to think of it, but there's lots of issues with that. For some reasons, it's tricky to get it to work. You might have lots of proxies along the way, and you could actually, as in this case, you could go blue, red, blue, and that's just not reasonable. So we actually had to abandon that and had to find something better. So what we eventually end up doing is we have each ray track which nodes it's already been on, and there's 2 methods in the paper where we talk about how you can do that. And then when we build a BVH over these proxies and trace this ray into it, every time we trace that, we always find the first proxy that is on a node that we have not yet been on. So we basically disable all the nodes with any hit program that we've already been on and find the closest one we have not. So take this scene, for example, similar to the one before, with this kind of partitioning. This is the proxies that we would have in this case. Every node would have that. And now assume we're tracing a ray off the green node, a secondary ray. Maybe we shaded the green palm, and that was a shadow ray or a reflection ray. And that's the ray we want to trace. So the first thing we obviously want to do is trace the ray on that green node. It doesn't matter what the first proxy is. We want to do it on this node because it's already there. Why would we send it anywhere else? Then after that, we mark the ray as I've been on green, so basically disable the green boxes, traces into the proxies and find the closest one. In this case, that's the blue one. It overlaps the same origin, and that's perfectly fine. It's the closest box, so we send to the blue node. The blue node intersects the blue geometry, and after that, marks the ray as having been on blue, traces into the proxies, sends to the red node finds a hit point, we shade the hit point, etc., 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 right? So very simple. It's actually a bad example in a sense, because in this case, the ray actually had to go through all of the ranks to finally find the hit point. But I think it's easy to see if you think a little bit about it. If the proxies are good, then in many cases, it doesn't. In many cases, the ray can very quickly narrow it down to 1 or 2 candidates that it has to traverse. And that's basically what we're after. So the rest of the paper, not of this talk, is about how you can put this entire idea into practice. We're talking about how you can do the actual scene partitioning, which is a super tricky problem. We're talking about how you can track previously visited nodes and how we build a full system with that. And again, I don't have time to talk about that, so read the paper. Just as a teaser of the results, again, full evaluations in the paper, maybe the most important thing is object space splits are way better for partitioning this kind of model data. You generally have much less data per node for a given number of splits that you have. And that means you can reach the same memory budget faster. And very often we can reach memory budgets that with spatial we just can't get at all, just because we have so much replication going on. It's also a way more general way of representing context, because you could move things around and that's fine. The boxes already overlap. It doesn't matter if they overlap more. So that is an important thing. A second interesting result is that with a good partitioning and good proxies, you can actually be faster than spatial partitioning, because if the proxies are tight, then I have less forwarding, and that means I'm faster. Super important is the proxies that we use, they don't have to overlap. They can actually also represent classical spatial partition. So our method is not an either or, it's actually a superset. You can use existing spatial data, spatially partitioned data. It works just fine. We do that in several follow-up projects. And finally, it actually works. It works great. Here's 2 screenshots from rendering this thing on 4 nodes with a total of 8 GPUs. You wouldn't actually need so many nodes for the object space partitioning. We only need it for the spatial partitioning as a reference. And it works great. You can interactively run through there. It's with path tracing. There's no artifacts whatsoever. Noise, of course, a path tracer. But other than that, it just works great. So with that, I'm at the end of the time. There's a lot of details that I glossed over. I refer to the paper. I'm also fully admitting here there's several issues that are remaining here, in particular in the systems design, where you can try to get more performance. And maybe the biggest one is this problem of what is the best partitioning. We show there are some good ones, and they're better than spatial, but we don't yet have a solid handle on what is the best one. If you're looking for a challenging problem, let me know. Here is one. So that is also something that needs some further work. But other than that, we're really happy with the system that we have and with the results that we get, in particular, given that it's a relatively crappy home internet. And so we are very happy with the results that we have. And with that, I thank you for your attention, and I'm open for questions.
Thanks very much, Ingo. Really interesting questions. Or interesting paper. Now let's see. who has questions. You can step to the mic with the button, the step to the mic button in the bottom right, and ask a question there, or you can type it. And if you type it, I'll read it off for Ingo. While other people are formulating their questions, I'll ask. So you get to the point where you've identified your proxies, you've built your proxies, and you know which proxies map to each rank.
Yep.
And then before you hand array off to that rank, in determining that the array needs to go to that rank for processing, do you put all of the proxies that pertain to that rank in a single subtree of a BBH? Is that how you know where it needs to go?
So right now, all of the proxies are replicated onto every rank. So every rank has all of the proxies, and they're all in one BBH. And each of those has basically a bit mask of all of the nodes that it is on, right? I said it's typically on one, but you could have things like the ground floor and replicate it if it's cheap. And then you trace array, and in the AnyHit program, you actually check these bit masks and say, hey, this thing is available on ranks 3 and 5, and I've actually already been on rank 3, so there's no reason for me to look at this geometry. I'll just kill that primitive and keep on going. And so the first proxy, the closest proxy that you hit that is not being rejected is one that you've definitely not been to yet and that you have to go to. That is the one that you get scheduled for.
Got it. Thank you. So here's a question in the chat. Is latency an issue as the array is sent over the network across nodes?
Yes, obviously. So first of all, we do not get like 100% GPU utilization. We are still very much bandwidth bound. There's things you could do to get performance up. You could have multiple different streams. You could have one set of streams that is shading and generating the new wavefront going out, while the other one is doing the MPI code to in and output. We're not doing that yet. There's actually a giant amount of systems work already in this. There would be like 2 papers just on that. So we haven't done that yet, but it would definitely be helpful to reduce this latency.
Thank you. Aaron, go ahead and ask your question live.
Hey, Ingo, really nice work. I was going to ask, is there anything you do differently for volume data, for example, as opposed to large mesh data in a system like this?
Yes and no. So we have a follow-up paper on that already. Well, it's not written yet, but we have several follow-up projects on that. One is on volume data, obviously. If your volume data, in most cases, if you have structured volume data, and most of the large data sets unfortunately are, then you don't actually need that much of it. You need just a spatial partitioning because the things don't overlap. And that's why I said I know it works for spatial partitionings, because we use that all the time for volume data. It gets a little bit more interesting once you have non-spatial partitions in the case of like fun 3D data with tetrahedral meshes, volumetric tetrahedral meshes, and they can overlap more. For that, we currently do some spatial partitioning, and that works just fine. We could also use this system to basically find the entry points to a mesh, then do the shading on that node, and then again use the system to find the next exit point. That is currently being worked on, but needs some re-engineering of the system. But I'm fairly sure it would work for that. And in fact, that's exactly one of the reasons why it was designed. And when I mentioned the generality of representing content, this kind of in situ application for visualization is exactly that. You do not want to repartition certain objects. You want to say, this node has this geometry, it overlaps other stuff, but shit happens. You have to be able to trace that. That's exactly what this is for.
Thanks. Next question is from Tammy Bubakur in the chat. You essentially defined proxies as bounding boxes. Would it make sense performance-wise to have more accurate proxies, geometrically speaking?
So yes and no. So the first thing is we have bounding boxes, but we have possibly multiple bounding boxes. So basically for large objects, think more of a voxelization. So we already get part of this benefit.
Okay, thank you. I'll give 10 seconds for any last questions.
And of course, if anybody has questions, send me an email.
Yeah. So thanks very much, Ingo and Steve. Great presentation, really illuminating ideas here. Let's thank our speaker one last time. All right. Thanks a lot, Ingo. Let's see. Quick reminder before we move to our next paper. Let's see. Now is the time to vote for the best paper award and the best poster award. The voting for that closes in 55 minutes. So you can click right here in the top right corner of the window where it says Show Best Paper Award Poll. Click there and vote for best paper. And then to vote for best poster, you need to go out of the auditorium and into the posters room, and there will be a similar button in there to vote. We will have 5 minutes at the end of the session where you can go and vote, but you can also go ahead and do it right now. Okay, our next paper is by Carsten, Benthin, Radoslaw, Drabinski, Lorenzo, Tessari, and Addis, Dittebrandt of Intel, and it's entitled PLOC++, Parallel Locally Ordered Clustering for Bounding Volume Hierarchy Construction Revisited. Carsten will be our presenter today. We kind of ran into one of the big downsides of virtual conferences is that people don't respect your time when you're not physically gone to the conference. So Carsten is not going to be presenting his paper live. We'll be streaming a pre-recorded presentation of the talk, but then with luck, Carsten will be out of his conflicting meeting by the time that ends, and we'll still be able to ask him questions live at the end. So with that, we'll turn it over to Carsten's video.
Hi, my name is Carsten Benthin, and today I'm going to talk about PLOC++, our new version of the parallel locally ordered clustering approach for constructing bounding volume hierarchies. This is joint work with Radoslaw, Drabinski, Lorenzo, Tessari, and Addis, Dittebrandt. Okay, so it's pretty obvious that ray tracing has become mainstream in the interactive/real-time domain over the last couple of years, and that the bounding volume hierarchy has established itself as the dominant underlying acceleration structure. Now, in the context of supporting fully dynamic content, the issue is that due to BVH quality reasons, one cannot always just update/refit the BVH, but instead needs to rely on a full BVH rebuild. That means the BVH construction method needs to be as fast as possible without sacrificing too much BVH quality, which together is a challenging problem. Okay, so over the last decade, many different BVH construction methods have been proposed, be it top-down, bottom-up, insertion-based, for binary or wide BVHs, focusing on CPUs, GPUs, or even custom hardware. It's not possible to cover everything here, so I highly recommend to have a look at the latest survey on bounding volume hierarchies for ray tracing by Daniel Meister and Shinji Ogaki. However, I would like to point out the previous work that our approach is based on, and that's the excellent parallel locally ordered clustering, or short PLOC approach by Daniel Meister and Jiri Bittner, published a couple of years ago. It's a pure GPU-focused approach, which is conceptually quite simple and elegant, and not too difficult to implement. It's also an iterative approach, which means a bunch of kernels per iteration are launched, which build parts of a binary BVH in a bottom-up fashion. So this iterative process is continued until the whole BVH is built. The original implementation already demonstrated quite decent BVH build performance, but in this talk, we're going to show how to make it really, really fast. So here's a quick outline of my talk. First, I'll do a quick recap on the original PLOC algorithm. Next, I'll introduce our new PLOC++ version, followed by a simple extension. Then I'll compare the original PLOC against PLOC++ and an optimized LBVH builder in terms of BVH build performance and quality. And finally, I'll conclude and present some interesting ideas for future work. Okay, let's have a look at the original PLOC algorithm first. It starts with a so-called pre-build phase. This phase gets a list of primitives, for example, triangles, as input. For each primitive, a so-called cluster representative, or short cluster rep, is constructed, which essentially is an Excel-aligned bounding box with a bit of extra data. Then for each cluster rep, a Morton code is computed, and the list of cluster reps is sorted based on their Morton codes. The final output of this is basically a spatially sorted list of cluster reps. With the sorted list of cluster reps as input, the iterative build phase begins. This phase essentially is divided into 3 parts. The first part performs an approximate nearest neighbor search for each cluster rep using a predefined search radius R. It does that by scanning R elements to the left and right of a given position in the sorted list and evaluates for each pair a distance function, which is simply the area of the pair's merged bounding boxes. In our example here, we evaluate the distance function at position C for the pairs AC, BC, DC, and EC. The nearest neighbor is the element for which the distance function is the smallest. In our example, let's assume for now the nearest neighbor for cluster rep C is A, and for D it's E. In the second part of the iterative build phase, which is called locally ordered clustering, or short LOC, we try to merge cluster reps with their respective nearest neighbor. However, only 2 cluster reps will be merged if they mutually agree on being their nearest neighbors. In other words, the nearest neighbor of my nearest neighbor needs to be myself. This merging creates a new cluster rep, which corresponds to creating an inner node in the inner binary BVH tree. So for our example on the right here, we create the new inner nodes A plus C and D plus E. So after creating the new cluster reps, the data of the 2 merged elements per cluster rep in the sorted list is updated. In particular, the element with the smaller index is overwritten with the newly created cluster rep, while the element with the larger index is invalidated. In our example, A is overwritten with A plus C and C is invalidated. D is overwritten with D plus E and E is invalidated. In the third and final part of the iterative build process, a simple compaction step is executed, which removes invalid entries from the sorted list, thereby reducing its length. This iterative process with its 3 steps is continued until only a single cluster rep remains, which means a full binary BVH has been built. Okay, now how's this algorithm mapped to the GPU? In the original implementation, each iteration requires 5 kernel launches. 1 for the approximate nearest neighbor search, which is by far the most expensive kernel. 1 for the locally ordered clustering phase, which is the second most expensive kernel. And finally, 3 kernel launches for the compaction, which relies on a prefix sum. Besides that, auxiliary arrays for storing nearest neighbor indices, valid flags, and for the prefix sum are required. It's important to note that the typical number of iterations required per scene ranges between 50 and 150, which together with the 5 kernel launches per iteration required causes quite some overhead and reduces overall BVH build efficiency. So now with our new PLOC++ approach, we are addressing exactly these bottlenecks of the original approach. In particular, we merge phases into a single kernel launch to reduce the number of kernel launches per iteration. We get rid of all the auxiliary data buffers, which saves memory and bandwidth. In particular, we reduce significantly the cost of the nearest neighbor search. And finally, we handle the case of operating on a small number of cluster reps way more efficiently. Okay, so let's go over these changes step by step. The first question is, how can we merge the nearest neighbor search in the locally ordered clustering phase? The simple idea is to operate on independent chunks of cluster reps. So let's assume for now the list of cluster reps is divided into equally sized chunks of about 1,000 elements each. in order to perform the locally ordered clustering step directly after the nearest neighbor search for a chunk I, we need to include additional elements to the left and right of this chunk. How much depends on the actual search radius, which in this example on the slide is set to 2. The additional elements are highlighted as orange in the yellow boxes to the left and to the right of this chunk. Now let's assume E would be the nearest neighbor of D. In order to ensure that D is also the nearest neighbor of E, we need to scan R elements to the left and right of E. So this means in total we need to scan 4 times R additional elements in addition to the cluster reps in chunk I. To ensure merging consistency when processing the chunks fully in parallel, we extend the previous merging criteria to only merge 2 elements if the smaller index is included in the current chunk. So for our example, the pair, this condition holds for the pair DE, but not for the pair AB, because the smaller index B is outside the chunk I. Okay, so the processing of independent chunks in combination with the merging of the nearest neighbor search and the locally ordered clustering phase has more advantages. What we can do is we can do parts of the compaction phase in this merged phase as well, which reduces the actual compaction phase to just a lightweight version. Also, we don't need the auxiliary arrays anymore, right? For example, storing the nearest neighbor indices or the valid flags. So this saves bandwidth and instructions. We can also assign a GPU workgroup, or in CUDA terms, a CUDA block, to process a single chunk and keep all required data in shared local memory. With all that, the number of required kernel launches is reduced from 5 to just 2 per iteration. So in the next step, our task is to reduce the cost of the nearest neighbor search. Obviously, if you have n elements, the cost of this phase is n times 2 times r. Again, we operate on a single chunk of cluster reps at a time, and in order to reduce the cost, we exploit the symmetry of the distance function, which again is the area of the merge bounding boxes. In particular, we try to avoid redundant operations. To illustrate these redundant operations, just look at this example. When we start at position A and scan to the right, we compute distance A and C, but we are doing exactly the same when we start at C and scan to the left to compute distance C and A. To avoid redundancy, we store the smallest distance and the nearest neighbor index in shared local memory and scan only to the right of each element. So now when computing, for example, distance A and C, we update the distance and nearest neighbor index for both positions A and C. And we have to do this atomically, as neighboring work items / CUDA threads could access the same data. In the end, this avoids all redundant computations and essentially halves the complexity of the nearest neighbor search. Okay, in the next step, as the list of cluster reps shrinks per iteration, we will come to the point when only a small number of cluster reps remains, which basically corresponds to building the top of the binary BBH tree. At this point, launching a kernel just to process a few hundred elements is pretty much overkill, as the cost of launching a kernel is bigger than the cost of performing the actual work. The very simple solution to this problem is to first test whether the number of cluster reps is below a certain threshold, for example, a couple of thousand elements. Then launch a kernel with a single workgroup. The single workgroup performs all phases of the iteration using fast barriers for synchronization. So this ensures that the number of iterations where we need full kernel launches typically stays under 50 for most scenes. So with that, we have covered all contributions of PLOC++, so I would like to present a simple extension to make it even faster. The extension focuses on reducing the kernel launch overhead even further and relies on the previous idea of using workgroups and barriers for doing the entire iterative process per workgroup within a single kernel launch. So what we simply do is to use the already existing Morton codes to extract m somewhat spatially independent partitions. What we do is we traverse the Morton codes top down in a breadth-first manner to extract these partitions. So in the next step, we launch a single kernel and process all of these partitions independently by assigning a single workgroup per partition, as shown here in this example. Each workgroup performs all required iterations and stops if the number of cluster reps per partition is smaller than a predefined threshold. As a final step, we launch a single workgroup kernel which fetches the remaining cluster reps per partition and compacts them to a sequential list again. At this point, the build process simply continues in the usual way with the compacted list. The advantage is that with this extension, the number of kernel launches is actually independent of the number of iterations required. However, there's a catch. The resulting BVH tree will differ from the one constructed by standard PLOC/PLOC++, as the nearest neighbor search is restricted to the elements in the partition. We call this entire approach PLOC++ two-level, as it uses a kind of an implicit two-level hierarchy. Okay, it's time for some results. So we coded everything with the data parallel C++ compiler that Intel provides with the OneAPI toolkit, and run everything on Ubuntu 2004 Linux. In terms of hardware, we used the pre-production Intel Alchemist G10 GPU, which is a kind of a big one, right, with 32 XE cores, 16 GB of DDR6 and full ray tracing hardware support. In terms of workgroup size, we use the maximum, which is 1024. And with respect to Morton codes, we used really big ones, right, with a 64-bit key and 32-bit index because of quality reasons. For sorting, we used an optimized LSB radix sort implementation. And as the default setting is to use the search radius of 16. Okay, so first let's have a look at the relative kernel runtimes using device timings. Excuse me. Device timings mean we only measure the time per kernel on the device, excluding any kernel launch overhead. I would like to point out the orange and red bar of the original PLOC approach, which correspond to the nearest neighbor search in the locally ordered clustering phase. If we compare this to the corresponding merged phase of PLOC++, which is the yellow bar, we see that the merged phase with the first and nearest neighbor search basically cuts the cost in half. Also, PLOC++ gets rid of the entire prefix sum part and uses only a lightweight compaction phase. What's interesting is that for PLOC++, the pre-build phase, which means Morton code generation, sorting, etc., has already larger cost than the actual iterative BVH build phases. So in this comparison, we show relative BVH build performance speed up of PLOC++ in its two-level extension versus the original PLOC implementation using host timings. Host timings include any visible kernel launch overhead. As speed of light reference, we also include numbers of an optimized 4D 64-bit Morton code LBVH builder, which can kind of be considered to be one of the fastest from-scratch BVH build approaches available. So now the graph shows that PLOC++ provides roughly a speed of 1.9 to 2.3x compared to the original implementation, while the two-level extension with its minimal kernel launch overhead increases the speed up even to 3x for some scenes. Okay, BVH build speed up is one thing, but the quality of the final BVH needs to be good enough to ensure high tracing performance. In order to test the real-world impact of BVH quality, we use the simplified diffuse path tracer as a benchmarking tool and compared the actual ray tracing performance of PLOC++ against our highest quality BVH builder reference, which is an offline CPU-based bind SH builder. Here, the graph shows that both PLOC++ and its two-level extension achieve 90%, roughly 90% or more of the ray tracing performance when we would use a bind SH builder, which is actually pretty good. On the other hand, the LBVH builder provides visible lower BVH quality and therefore lower ray tracing performance. In conclusion, PLOC++ and its two-level extension provide a significant speed up in terms of BVH build performance compared to the original approach, while retaining high BVH quality and ray tracing performance. But in my opinion, the biggest advantage of PLOC++ is simple implementation. Nevertheless, we will provide the full source code of our implementation in an experimental branch of the upcoming MP4 release. In terms of future ideas, I mean, there are many ways to optimize the current approach, right? We could apply even faster nearest neighbor search. We could compress the cluster reps to save bandwidth and memory footprint. We could apply rebraiding techniques to the two-level approach to gain further quality, etc. There are many optimizations possible. Okay, that's it. Thanks a lot for listening, and I now take your questions.
Very much, Carsten. Okay, and we have Carsten here live, and he appears to be wearing the same T-shirt, so we have continuity. Let's see. Thanks, Carsten. I'm glad you could make it in person.
Sure.
Just one quick clarifying question while other people are formulating their questions. What is the fourth dimension in the LBVH that you compared to in the results?
It's the size of the triangle.
Okay.
So you have the position, and the fourth component is the size. So you get, for most of the scenes, you get better quality with that.
Cool. Thank you. All right. Other questions? Okay. Here's one in the chat. Have you compared the relative speed up on other GPUs? Note, I'm not asking Alchemist versus others comparison, but PLOC++ versus other builders on other GPUs.
Let's put it that way. We plan to do so, but we haven't gotten around to do it. But it should be really straightforward. I mean, the implementation is really simple. So a pod shouldn't take too long. That's for sure. But we tested other algorithms also on Alchemist, right? Be it ATR, BVH, and other variants.
Okay, cool. Next question also in the chat. Maybe I missed it in the talk, but did you consider leaf geometry other than triangles?
No, but the entire build process is kind of independent of the triangles, right? It just takes a bunch of bounding boxes as input, right? And you can generate these bounding boxes from any kind of geometry data, right? So the triangles is just the typical, let's say, set of models that we use, right? But it's completely independent of actually being triangles.
Okay, next question. What proportion of gains do you attribute to the reduced kernel launch overhead versus other algorithmic optimizations?
Could you repeat the question? I missed it at the beginning.
Okay, what proportion of the gains do you attribute to the reduced kernel launch overhead versus other changes?
So I think the question goes whether games are really affected by the kernel launch overhead. I'm not an expert in games, so I'm not sure how much, let's say, pipelining is done to kind of hide this kernel launch overhead there.
So gains, as in how much of the speed up is from reducing the kernel launch overhead
okay.
versus other things.
So usually it's depends on the model, but it's 1.3 to 1.4x what you save. If this makes sense.
Okay. Yep.
It depends on the number of iterations, right? The more iterations you need, the more kernel launches you have, right? And the more you will save from reducing, let's say, using the two-level extension. And for example, in the paper, we used the Rangholt scene, which has the lowest number of iterations. So the kernel launch overhead is also the lowest, while I think the Bistro scene requires the most iterations and therefore sees the biggest gains with the reduced overhead.
Okay, so the number of kernel launches due to iterations is a big part of what you're solving here.
Exactly. So we reduce the number of kernel launches per iteration in the standard PLOC++ plus approach, and we reduce we get to almost 2 or 3 kernel launches only with the extension. So this is independent of the number of iterations.
Okay. Next question. Why does the 2-level version sometimes give better performance than the 1-level version?
This is a very good question.
And I assume that means ray tracing performance, not build speed.
Yes. So the 2-level approach relies on the Morton partitionings. And depending how the Morton partitionings are, you get, let's say, a different top of the tree, right? And there, sometimes it seems the Morton partitions do well, and sometimes they don't, right? It's really hard to say what exactly is the reason, but I think the main point is that we don't lose much quality with the 2-level approach. If it's even better for some scenes, that's great. But I cannot really pinpoint you to one exact reason. It really depends how the partitions are kind of dividing the model. And the problem with the Morton's code, they only look at the centroids, right? They don't take into account the spatial extents of the bounds.
And also, any time you map 3 dimensions onto 1 dimension, you're going to have discontinuities, right?
Yes.
And it's just kind of luck where those discontinuities fit you.
Absolutely.
Yeah. Which just an aside, this makes me think maybe the world, somebody ought to try other space filling curves because they have different properties, right? They have the discontinuities in different places and different magnitudes of discontinuities.
Absolutely. We actually tried Hilbert curve, but it didn't make much of a difference. I mean, Hilbert avoids these kind of Z structures of the Morton code. But for Block++ or Block in general, it didn't make any difference. Most likely because the search window is so big that you kind of cover these Z steps.
Thank you. That's good to know. Okay, let's thank our speaker one more time. Thanks, Carsten.
Thank you.
Okay, our last paper in this session, the last paper of the conference, is by Andrew Adams of Adobe Research and Dillon Sharlet of Google. It's better fixed point filtering with averaging trees. Andrew will be our presenter today, so go ahead, Andrew.
Hi, thanks for the introduction. I'm Andrew from Adobe Research, and today I will be telling you about joint work with my friend Dillon, who was at Google for this work. Now, Dillon and I are friends for many reasons, but what truly bonds us is our shared love of fixed point arithmetic. And one day we were talking about fixed point math, as we often do, and we discovered that a fast approximation that we like to use for some very common filtering operations actually produces higher quality output than the thing we were approximating. So this is a free lunch. It's faster and higher quality at the same time. It's a simple idea, and the paper is short, but it's something that we felt everyone who pushes pixels for a living needs to know. But first, why do we care about fixed point arithmetic at all? So Dillon worked on Google's HDR+ camera pipeline, and I work on Adobe Photoshop. And I imagine a lot of the GPU programmers here are used to everything being floating point, but in the land of photography, integers are king. Integer math uses less power, it has higher throughput on many processors, and in fact, some of the DSPs we use in photography don't support floating point at all. So when I say filtering, what I mean is taking weighted averages of integers. Why might we do that? Lots of reasons. If we want to reduce the size of an image by a factor of 2, maybe because we're constructing an image pyramid, then each output pixel might be the average of 4 input pixels. If we're bilinearly upsampling an image by a factor of 2, maybe in the same pyramid-based algorithm, we might use a 9331 filter, where each output pixel is that weighted average of the inputs. So at the top left output, the weight is largest on the top left input, lowest on the bottom right input, so those weights are 9 and 1 respectively. And at the top right output, the 9 goes to the top right input, and so on. And this 9331 filter rotates to produce each output, dividing by 16 each time to make it a weighted average instead of a weighted sum. Filtering is, of course, very common in 1D too, often because you're doing separable 2D filtering. Popular kernels are the rows of Pascal's triangle, perhaps because they're the binomial approximations to the Gaussian, but more likely because they sum to powers of 2, so the division is cheap. The even rows are commonly used for resampling, and the odd rows are often used for blurring. And if you think the odd rows are used for resampling, then we can fight after the talk. Now, in the integers, none of these weighted or averaging operations can be done exactly. With integer division, there's always some remainder you need to handle. So let's return to the first example and consider the math in the integers. We can't compute the exact average of 4 values. One option is to just round down, compute the floor of the average. This is obviously going to be darker than the true average because we threw away any remainder modulo 4. Well, let's quantify how much darker. If A, B, C, and D here are independent uniform random variables, then the discarded remainder after we divide by 4 has an equal chance of being 0, 1, 2, or 3. So the output will be, on average, 3/8 of an intensity level darker than the ideal output, what the floating point output would be. We also care about the peak absolute error, which is the maximum difference from the ideal answer. And the worst case for this average is when the remainder was 3, leading to a peak error of 3/4 of an intensity level. We can do better if we round to nearest instead of rounding down with ties rounding up, which can be expressed like this. You just add a +2 in the numerator. We still introduce a little bias because ties round up. This time the bias is +1/8. And the peak error is a little better. It's 1/2. That's as good as the peak error can possibly be, actually, because our output has to be an integer, and sometimes the correct output is exactly halfway in between 2 integers. But what we really care about is the bias, not the error, and I'll tell you why. Bias creates artifacts that make photos look worse. Here's a picture of a mountain scene, and we're going to zoom in on this crop in red. On the bottom left is that crop brightened a little, and it has something subtly wrong with it that's objectionable to the discerning pixel peeper. There are these purplish blobs in the chrominance channels on what is supposed to be gray granite. Now, Dillon traced these back to bias being introduced by filtering operations at high pyramid levels of a pyramid-based algorithm nested inside a long, complex camera pipeline. If we use unbiased filtering instead, the blobs are gone and the granite is gray again. So those blobs were produced with ties rounding up, which is by far the most common way people do things. Photoshop does filtering with ties rounding up. LibJPEG does filtering with ties rounding up. The video encoder and decoder you're using to watch this talk almost certainly does filtering with ties rounding up. In fact, it's so common that some instruction sets support it explicitly. And if you'll indulge me, I'll show you what the ARM instructions are for computing this quantity. Don't worry, I'm going to very slowly walk you through this. So first, we're using SIMD instructions because presumably we don't have a single instance of this problem. We're computing an entire image worth of output. So we should compute it using SIMD vectors. ARM's vector registers are 128 bits wide, which means they can hold 16 8-bit values each. So first, we'll load a vector worth of each input. So each of these instructions loads 16 8-bit values. Then we'll compute the sum of the first 2 inputs, A plus B. And this takes 2 instructions. That might seem like a trivial detail, but it's going to turn out to be the key reason that our technique is faster. So it takes 2 instructions because we need to widen to 16-bit integers so that the sum doesn't overflow. And 16 16-bit values uses 256 bits, which is 2 SIMD registers. And we need 1 instruction to compute each. So uaddl computes the first half of the output, and the imaginatively named uaddl2 computes the second half of the output. Then we use 2 more instructions to add the third input, 2 more to add the fourth, and then we do something called a rounding, narrowing, shift right, which adds 2, divides by 4, and converts back to 8-bit, all in a final pair of instructions. So the ARM instruction set is highly specialized for this computational idiom, as are many DSP instruction sets. Finally, we store the output. But there's another way to compute an average of 4 values, one that doesn't require 16-bit intermediates, which is going to immediately halve the number of instructions we need. We're going to construct it out of pairwise averages, because unlike a sum, an average of 2 8-bit values is still 8-bit. Averages can't overflow. So first I'll introduce some notation to keep ourselves sane. I'll say that up arrow applied as a function is the average of the 2 values. And down arrow, sorry, is the seal of the average of the 2 values, the average rounding up. And down arrow will be the floor of the average rounding down. So these instructions are rarely used, so you may not have heard of them, but most CPU and DSP instruction sets support each of these operations as a single instruction without requiring any wider intermediates. x86 weirdly is missing the rounding down variant, but you can emulate it pretty cheaply with some clever bit tricks. So we can compose these pairwise averaging operations to compute approximations of more interesting averages. So for an average of 4, we can compute the average of A and B, then the average of C and D, and then we can average those averages to get an approximate average of A, B, C, and D. If we round up on the first 2 averages and we round down on the last average, then that neatly cancels out any bias. But this approximation throws away information at that intermediate step. We dropped a bit on the first 2 averages. So surely the peak error is going to be worse. How can we find out? Well, I can't easily figure out the peak error in this case on paper, but fortunately we have computers, and it's easy enough to just exhaustively check every possible set of inputs and measure the peak error. And when you do that, to our great surprise, we found that the peak error is as good as you can get. This is very strange. This is the point at which we thought we might be onto something. The assembly is just 3 arithmetic instructions for the 3 averaging operations. And that's the minimum number of instructions required to combine 4 inputs. So this is optimal in every sense. It's the fastest possible way to average 4 inputs, and it produces the best quality output according to our bias and error metrics. There's no trade-off here. Whenever you want to take an average of 4 integers, you should do this. So to recap, if you want to compute this average of 4 values, you should instead compute this, which we can represent as a tree of averaging operations, where the leaves are the inputs and the inner nodes are either average round up or average round down. Okay, let's generalize to different filters now. Let's say we want to compute a 1-to-1 filter instead, where we have A plus 2 times B plus C divided by 4. We can just take our previous tree and replace D with an extra copy of B, so that now B appears twice in the leaves, so it has double the weight. It's no longer obvious, to me at least, that this is unbiased, because the 2 leaves are now correlated with each other. Also, there are multiple ways we could have done this. All that matters is that B appears twice at the leaves and A and C each appear once. So at first, the tree on the right actually looks like a better approach. We're averaging a value with itself, which means we can simplify it to this, which uses 1 fewer instruction. And in general, that is a good thing to do. However, in this specific case, if we exhaustively check bias and error, then we find that the tree on the left is optimal, but the one on the right is biased. So if you want to take a 1-to-1 filter, use the averaging tree on the left. And that brings us to the general algorithm for finding these trees, which I'll illustrate with a 9331 filter, which, as you recall, is for bilinear upsampling. So first, we place each input at the leaves of a balanced binary tree a number of times proportional to its coefficient. So we have 9 copies of A, because the coefficient on A is 9, 3 copies of B, 3 copies of C, and a single lonely D. Then we'll just try all permutations of those leaves and all possible rounding directions for the inner nodes. Each of these is going to have a different bias and error, and we can just exhaustively compute bias and error of each until we find an optimal tree. This one rounds up everywhere, so unsurprisingly, there's a strong positive bias. So if we flip some rounding directions, things can get a little bit better, more tweaking of rounding directions. And finally, if we shuffle the inputs a little, we can find an optimal 9331 tree. So this is just a big brute force search. There are a lot of symmetries you can exploit to make the search faster, though. The big one is that averaging is commutative. So there often aren't that many meaningfully different permutations of the inputs. So now that we have our optimal tree, we can simplify it by collapsing any nodes that average a value with itself and checking for common sub-expressions. Now, there weren't any in this case, but when there are, this turns our tree into a directed graph. There are 6 inner nodes, so now this is a 6-instruction way to compute a perfect 9331 filter. So compared to the standard way of doing a bilinear upsample, this is about 60% faster on ARM and x86, and it introduces no bias, so the output's a little better. So 2x upsampling is, with bilinear interpolation, is very, very common. So we were very happy to make it 60% faster. We repeated this search for all the filters I mentioned at the beginning of the talk and a few more. And in every case, we were able to find an averaging tree that has 0 bias, minimum peak error, and uses fewer instructions on ARM and x86. So these are the measured speedups on ARM and x86 for applying these filters repeatedly to an array in cache. They're just unconditionally faster, sometimes by a lot, especially on x86, where there are no widening add or rounding shift right instructions. We also have some evidence that this is a good thing to do from some real-world usage. The image I showed you earlier is from a real camera pipeline that has been used to take billions of photographs. This is the HDR+ pipeline used in Google Pixel phones. If you recall, bias at the high pyramid levels was causing purplish blobs on the gray granite. And on the right, Dillon replaced 59 separate filtering operations in the pipeline with our averaging trees, and the blobs are gone and the granite is gray. So this not only improved the quality of the output, but it also sped up the affected pipeline stages by 11%. So whenever you can use an averaging tree, you should. They're faster and better. Unfortunately, you can't always use an averaging tree. First, we've only shown optimal averaging trees for 290 different filters, including the ones in this talk. If you run our code for longer than we did, it will spit out more. And the list of filters along with pseudocode for each is in the supplemental material for our paper. We also have about 1,000 more trees in supplemental material that are unbiased, but don't have the minimum possible error. Second, the coefficients in the filter must sum to a power of 2. If you have filters that sum to other things and you need to divide by denominators that are not powers of 2, I know a whole separate family of tricks for that, and I'd be happy to talk to you about that offline. Finally, the coefficients of the filter must be positive, which rules out many useful filters that have negative lobes. But the overall message of our paper is very simple. If you're doing fixed point filtering and your filter is on our list, then use an averaging tree. It's faster and higher quality at the same time. And with that, I'd be happy to take questions.
Very cool. Thanks, Andrew. So this paper is related to the other two only in the sense that it uses a tree data structure at the theoretical level. But a lot of us here love integer math as well, being hardware people. So this fits right in. That's great. Let's see. Okay, here's our first question in the chat. And you can give your questions verbally with the step to the mic button or in the chat. The question is, have you considered similar techniques being useful for floating point operations and involved roundoffs?
Not especially, no. I mean, in floating point, so I would say, first of all, another really common unbiased way to do fixed point filtering is with ties round to even. It has a few minor downsides. The main one is that it's more expensive. But in floating point math, I believe you can just set the rounding mode to ties round to even. And normally you have so much excess precision that that's perfectly adequate. So we haven't really considered these sorts of tricks for floating point for that reason.
Though if you're using an aggressively reduced precision floating point, like FP16 or FP8 or bfloat 16, this might become more important.
That's true. I have not thought about that.
Okay, next question. Okay, these are getting hard for me to read here. Let's see. Okay, it feels like there should be some mathematical property that can help design these trees directly without brute force search. For example, intuitively, I might expect average down plus average up, as in the motivating example, might scale up. How hard did you search for such a mathematical property?
Yeah, so if you're combining two subtrees and they have completely disjoint inputs, then they're sort of mathematically independent. You know the final bits are uncorrelated, and you can compute closed form what the bias is going to be. But as you can see from the slide, we have directed graphs rather than trees with disjoint inputs. As soon as you have sort of overlapping sub-expressions being fed as inputs, it becomes sort of combinatorially hard to track what the bias is going to be. And it's really easy to just try every possible set of inputs. In a sense, look, this paper is much more of a discovery than an invention. We found that these trees exist. We don't know exactly why they exist.
But they're pretty darn cool. Okay, Jonathan, you want to ask your question?
Yes, great talk, great contribution. I was thinking about the geometry, well, the topology of these trees you've derived. So some of them are clearly symmetric. I'm looking at the slide right now. But so the rightmost one is asymmetric, but I would imagine that if you were to flip the configuration, it would be invariant, right? Would you get the same bias and error?
So you would get the same bias and error.
Yeah.
The other thing you can do is flip all the rounding directions, and you get the same bias and error. It's also invariant to that.
Okay. Okay.
However, these filters are not always commutative. Actually, I have a backup slide that might be interesting. So we have a 1-1 filter, which is odd because it's an average of two values. And if you do ties round up, you get the thing on the left. If you do ties round to even, you get the thing in the middle. Something objectionable about that is the even valued outputs produce much wider bands than the odd valued outputs. And on the right, we have our averaging tree. And it's unbiased, and it's very fast, but it's not commutative. So that the transpose of this is not equal to it.
Yep.
So if you really care that two filter taps with the same coefficient, it should be invariant to permuting those, then you might need to add a layer on top of our averaging tree, or maybe not use an averaging tree. But for the applications that we're aware of, that property doesn't seem to matter.
Yeah, that's very interesting. Thank you.
Thank you. Okay, one last question in the chat. Lots of GPU hardware includes hardware texture units that perform filtering. Do you think this optimization might improve those hardware filters?
Yeah, at the hardware design level, quite possibly. We haven't, oddly for this conference, but we haven't really thought about GPUs because on GPUs, the floating point units tend to be much higher sort of provisioned than the integer units. I know on much older, like the very first versions of CUDA had various packed fixed point operations that were sort of shuffled away. And if you try to use them now, then it emulates them instead. But I hadn't considered that you might actually want to design filtering hardware using trees of averaging operations. It's possibly true.
It's an interesting potential direction. All right, looks like we have one last question from Dillon. Go ahead.
I'm actually the co-author of this paper. I was just going to mention that another issue with using this for GPU hardware is that typically that hardware, like you don't know that it's a 2x upsampling, for example, or like where the things are going to be sampled. Like, so this approach is used when you are doing like some kind of like fixed rate resampling, whereas the GPU resampler is kind of just very dynamic. They don't know that that's going to happen ahead of time. Maybe there's other parts of the GPU that do that, but I think just like the generic thing that I assumed we were talking about here, I think it'd be hard to do.
Right, yeah, because the topology changes as a function of the filter weights.
Good point. Okay, thanks a lot, guys. Andrew and Dillon. Okay, let's all thank our speakers one more time. Thank you. Okay, so that concludes this paper session. Over the next 5 minutes, make sure you've voted for the best paper award. Click the button in the top right of the auditorium screen to get there, and then go out of the auditorium, go to the posters room, and do the same thing there to vote for the best poster. And we'll be back in 5 minutes with the results. I think that's what's next. Sorry, I'm kind of spacing it, but go vote for best paper right now. Sorry.
Hey everyone, I'll be presenting the results of the student competition 2022 to you now. So first of all, I wanted to give a brief overview again, like what the actual competition was about. So the challenge that we set out was to optimize a real-time path tracer, and the goal was to optimize the quality while staying in a strict performance budget. So the rules were the shader was, or the path tracer was originally written in ShaderToy. So it's kind of like a full screen shader that is run for each pixel, and you can have multiple passes. And so the participants had to also submit their shaders in ShaderToy. And they had to stay within 2 times the runtime of what our shader originally had. So basically just increasing the sample count would not have been a qualifying submission. And then we took these shaders and we compared them to a converged 100,000 samples per pixel reference image. And so having these submissions like being submitted in ShaderToy puts quite a few limitations and challenges for the participants. So first of all, like you cannot, or foremost, you cannot store additional data very easily. So ShaderToy does not allow you to upload user data like textures. So everything that you submit, it must be part of a shader that is executed on the GPU. In total, we had 9 submissions from 8 different countries. So we had international participation, which makes me very happy. And we also had like a quite large variety of different techniques to improve the quality. So we had lots of interesting submissions. Like in many of the submissions, we saw more efficient scene intersections. So basically placing like additional bounding boxes around the characters that are in the scene, better traversal, pre-computing some of the matrices that were potentially computed on the fly. Then we had submissions that improved the sampling strategies. So basically being more smart about selecting the light sources. So in the scene, there were 4 cube-shaped light sources, and the original shader just randomly selected one of the faces. And you can imagine that, of course, many of the samples then just ended up on the wrong side of the cube. So some of the submissions improved these with different approaches. Then we had one submission that essentially pre-computed all of the lighting and baked it. Then we saw submissions that did denoising, so special temporal denoising techniques. And lastly, we also saw temporal filtering as a very common component that just reused samples that were computed in previous frames and reused them. Again, that sounds probably more straightforward than it is in ShaderToy, since you have to juggle with these different buffers, and you are only like you can only have 4 passes in total. To score these methods, so first of all, they of course had to stay within our performance bounds, which all of the submissions did. And we then compared these to the reference using the flip error metric set to 37 ppd, which is basically equivalent to looking at these images at a desktop screen. All right, now for the results. So this is the most typical result that you would see when you open these shaders. So unfortunately, many of these crash the browsers. So I want to put like a brief call to action at this point. So please, to anybody that is involved with WebGL browsers or anything, please, please, please work on this. I don't think it's acceptable in these days that like you can write a shader, execute it in WebGL, and crash the entire browser. It's first of all very painful. We have many tabs open. Maybe we're editing some text somewhere and it crashes, we can lose work, and it's obviously also a huge security risk. What we also saw was that Angle, which is the backend that is used, for example, in Chrome, which translates OpenGL into direct 3D shaders, is not a very good substitute for OpenGL, and all of the participants manually had to change their browser settings to even be able to compile the full shader that we provided. Of course, it very aggressively inlines, and basically for each of the bounces, And for each of the intersection tests that were computed, it would blindly inline the entire scene. So all of the primitives are millions of times in the shader code. So that's clearly a problem, of course. All right, so now really for the results. So these are the different flip error metrics that we saw. And in the flip score, a lower number means that you are closer to the reference, so smaller error. And we had two submissions that were very close to each other, the runner-ups. So we have two honorable mentions with a flip score of 0.11. And then we have our winning submission with a flip score of 0.05. And yeah, that score means that it's almost impossible to distinguish the reference. And I'll show these submissions. Yeah, here we can see the two honorable mentions by Akshay Jindal and Arthur Pereira Valla Firmino. So congratulations to both of you. Both of you will be awarded with an Intel Alchemist GPU. For both of these submissions, they used SVGF for denoising, which again is not exactly trivial to implement inside of shader toys. So there's like some fancy packing and unpacking going on in Akshay's submission, for example. And Arthur also additionally worked on better performance by like optimizing the intersection routine, and also by just configuring the path tracer a little bit different, like removing bounces that are not necessary, using different random number generator, which allowed him to use higher sample counts. And now for our winner. So this is what the winning submission looks like if you open it with the wrong browser. And so again, this is coming back to this whole WebGL story. And the reason for this is, so here you can see actually the source code of the submission. And so this submission used a pre-baking of all of the lighting. And so it actually executes neural networks for each of the pixels that are embedded inside of the shader source. So you can see like it's these several thousands of lines of code in like multiple files. And so this definitely stress tests the compiler. But in the end, if you look at the submission, you get this stunning quality, which is just impressive. So congratulations to the winner, Yu Chang. Unfortunately, I'm sorry for butchering the name. Yeah, huge congratulations. I'm very impressed by this submission. It looks just stunning. It looks like the reference and runs faster than our original shader. So you will be awarded an Alchemist GPU and additionally the cash prize of $750. So congratulations again. All right, with that, I want to thank everybody that participated in the student competition, and also the people that made this possible. So Christoph Peters and Thomas Müller, who initially reviewed the path tracer for me, and yeah, of course, to my co-chair, Angelo Patney, who helped me out a lot as well. So yeah, check out all the submissions on the linked website. And if you participated in the competition and have feedback to share, please send it to our student competition alias. I'd be curious to learn like areas where we still have to improve to make it even more fun to participate. But overall, I hope it was as fun for you as it was for me. Thank you.
Hello, everyone. I'm going. Oh, yeah. Thank you, Christoph. Yes, we're in the process of finalizing the slides for the awards. So we'll ask you to be a little more patient. We should be ready in less than 5 minutes. So see you very soon.
All right. Well, thank you for sticking around till the end of our virtual HPG. And this is going to be the last session of the virtual part of the conference. It's going to be the awards and closing with an asterisk, because as you know, we have the virtual conference this week and we will have the in-person event. I'll mention it again before we end it. But let's jump in and get into our award ceremony, starting with our best poster awards. And Jonathan, you can get on stage.
I'm not going. Why am I on my own here? Can you guys hear me? Okay. So unfortunately, I don't know who won the best poster award. I'm gonna discover it with the slides, but I can't see the slides. So let's hope they'll come back.
The slides. All right, I'm guessing we're gonna have to try this one more time.
Okay, I can see the slides. Okay, so the winner for the best poster award this year is
unfortunately not showing up in the slide.
Okay. Yeah, that's you can feel the stress. I'm guessing Jeng is changing the font or the color, I suppose. Please don't fall asleep. Yes. What is going on? I'm sure Jem is picking the best font to display the result, and it will look beautiful. As for me, I'm trying to act cool. Well, I have no clue of what is going on.
Hey, Jonathan, we're adding the best paper to the slides right now, so it'll be ready in just a second.
Okay, okay. Well, please try to act cool with me then. Don't leave me on my own.
I like all the instruments, the drum rolls.
Yeah.
Appropriate.
Okay, the best poster award goes to Triangle Bisection Tessellation with Fractional LOD from Imagination Technologies by Peter Smith-Lacey and Simon Finney. Huge round of applause. And so you guys get to share an Intel Alchemist GPU. I guess you can show it around in Imagination Technology or in your office, and tell us, please share with us the reaction. So with that being said, I'll hand over to Joseph, who's going to announce some awards for Test of Time and papers, I guess.
All right. Happy to move on to the Test of Time Award. So we looked at the year 2012 HPG, looked at the papers that had seen some recognition from the community over the years, over the past 10 years. And we selected 3 papers that we thought were worthy of recognizing this test of time that have clearly had an impact on the high performance graphics and graphics community more broadly. And Jem, if you have them on the slide, the first one is Maximizing Parallelism in the Construction of BVHs, Octrees, and KD Trees by Tero Karas. The second one is Adaptive Scalable Texture Compression by Jon Neistad, Anders Lassen, Andy Tomianowski, Sean Ellis, and Tom Olson. And then the third one is Clustered Deferred and Forward Shading by Ola Olsen, Marcus Billeta, and Ulf Assarsson. So yeah, well-deserved round of applause for each of these papers and their authors for the great job, and these papers truly have stood the test of time. Next, throughout the conference, the poll has been open to vote for the Wolfgang Strasser Best Paper Award. It's named in recognition of Wolfgang's great contributions to the HPG community over the years. And the first place will get $1,000 recognition. And again, Intel Alchemist GPUs will be awarded. Now, for these in the poll, we ended up with a tie for third place. And so in whatever arbitrary order Jem decided to place them on the page, we have Virtual Blue Noise Lighting by Daniel Lee, Wenyo Wang, Bachilun, and Chen Yuxo. And also Better Fixed Point Filtering with Averaging Trees from Andrew Adams and Dillon Sharlet. So congratulations. Now in second place, we have, let's see, it looks like Data Parallel Path Tracing with Object Hierarchies by Ingo Wald and Stephen Parker. Congratulations. And then finally, in first place, we have Software Rasterization of 2 billion points in real time by Marcus Schutz, Bernhard Köbel, and Michael Zimmer. Excellent work. Now, a reminder that these papers are being published in the Proceedings of the ACM on Computer Graphics and Interactive Techniques, and they will appear, I'm told, in another 4 to 6 weeks on the ACM Digital Library. They will all be open access and available. We have linked to the majority of the papers, the author preprints and the author pages on our website. So you can go there to grab the papers, and many of the slides are showing up as the authors provide them, if you're curious in the slides. As well, the YouTube videos are available on our YouTube channel, and so you can go back and watch the presentations, catch any that you may have missed.
All right, thank you. And one more time, I would like to thank all our sponsors for their generous support for our conference. Let's have a round of applause to Intel, the Azure Lab, Unity, and Activision, Gavi, AMD, NVIDIA, and Chronoscope. And before we go, I would like to again remind you all that we have a named person event. If you can attend, if you're going to attend SIGGRAPH, do not miss that. We'll be there all together. 100+ people already signed up, and you should too. And if you're thinking, if you're not sure, please make a decision quickly, because the price is going to go up a little because we need to know the number. And remember, we're going to get together. We're going to have a reception, but also we're going to have a wonderful keynote. And one more thing, if you register for HPG and you're here, I'm pretty sure you're looking forward to your Cornell boxes. They're going to be on the way. They're under construction right now, and they're going to be on the way. And I would like to once again thank the works of the organization committee. We've been meeting pretty much every week for about a year, putting this conference together for you. I hope you've enjoyed it. Thank you all. Don't worry, I won't bring them up on stage one by one again. That's not happening. And I would like to thank you all for attending HPG, for being a part of this community. This has been great, and I'm hoping that I'll see at least some of you in the in-person event. Thank you all.